Welcome everybody. This is the second super summer session of a series of four. Our first was in June on stepping into the contractor's boots, and we're now getting into geotechnical uncertainties with this session, and we have a great lineup here. So the second session is, like I said, focused on geotechnical uncertainties and managing risks, and recognizing that having information up front before we get to construction is really one of these critical areas where traditionally investigations have focused on design, and where we begin early on getting information during the design process. We sometimes overlook the fact that we need information for the construction aspects. And so this whole series is focused on constructability and construction decisions, and we're going to be talking about geotechnical risks and geotechnical uncertainties during this session. We do have a few coming up, bridging the gap on communication, communicating these for construction needs, and then finally a forum that is specific to owners, and it's really a workshop atmosphere where we're going to make this happen, find out where our gaps are, where we need to improve our processes and procedures so that we can incorporate these construction needs for our investigations. So for today, what we're going to be talking about are those common problems that we do experience during construction related to geotechnical uncertainties, and some of the applications, the problem-solving applications, and the characterization of our conditions using A-GaME technologies, and then case histories that illustrate these points, and to both A-GaME technologies and the types of problems that we have. So just want to let everybody know that this session is going to be recorded, and we're going to have discussions both mainly during the second part of this session. So in the afternoon at 2 o'clock Eastern, we'll really have a lot of discussion, but at any time we might have discussions as the presentations this morning run through, and may have questions, but just recognize that the opinions that are shared here are of the individuals, not necessarily of FHWA or its contractors. So just be aware that we are having a discussion here, and we're talking about opinions throughout. We have recently have a new site. If you're not aware of the new A-GaME site, it's located at the geotechnical site. And Mary just put that site in the chat pod. It has a lot of new information and links to it, and we've been working on a number of social media and other videos that are very informative and appealing to not necessarily geotechnical engineers. They are, but I think they resonate with a lot of people, and they're a lot of fun as well, but very informative videos and social media content that can be found there. And if you want to keep informed of A-GaME activities, you can sign up at that website on the toggle, or the at the very bottom of it. So please do that. So we'll get into our session now. I'm Ben Rivers. I'm with the Federal Highway Administration. I'll be moderating and presenting today, and with me, Mary Nodine with GEI will be helping me moderate as well. Derek Dassenbrock may come in later on today to help us with moderation during the discussion as well. We have a number of speakers lined up for this first part. We've got Phil Sirles and Doug Lehman, and we have Gerald Verbeek, Mike Rodgers, and Rob Garfield. And later on, we have Jim Cupperson from Washington State DOT, and we have Andrew Fisk as well. And like I said, I will be presenting during that session too. So I am going to now get things rolling with Phil. Phil, if you want to take charge, I'll stop sharing. You can take charge, and I will do some introductions. So our first speaker is Phil Sirles with Collier Geophysics. Phil is the operations manager of geophysical services performed in the Colorado office of Collier Geophysics. He has a broad range of experience in engineering and environmental geophysics with over 35 years experience. He has extensive experience in seismic, electrical, electromagnetics, and GPR, or ground penetrating radar, and he has been involved with the FHWA A-GaME initiative since it started in 2018. With him, and later on, I think Doug will be joining us for the discussion and maybe presenting as well here. Mr. Lehman is a senior geophysicist and hydrogeologist with Collier Geophysics and is located in Austin, Texas. Mr. Lehman has 35 plus years of experience and has overseen a variety of hydrogeologic investigations and groundwater modeling. He has designed and managed numerous surface and downhole geophysical investigations for various engineering and environmental application. He serves on a leadership role in AEGIS, or Environmental and Engineering Geophysics Society, and he is also associated with the Association of Engineering Geophysics, or AEG, including being the standing current president of AEGIS Foundation right now. So with that, Phil, Doug, welcome, and you have the floor. And you're on mute, Phil. Phil, you're on mute. Can you hear me, Phil?
Can you hear me?
Yep, I can hear you now.
Okay, is my screen still showing?
I have a, I think I do not see your presentation. I see a screen image of.
I love how we practiced all this and then it just went right away. Seems to happen. I had it all ready and set to go. So let me get a little bit of a reset here.
Yeah, I'm not seeing your presentation yet.
Yep, I got to get it back up again here. Come on. Something is not working right in my. How about now?
We're seeing it.
You're seeing my opening slide.
Yep, you're good to go.
Okay, I apologize for that little hiccup there. It's a pleasure to be with you all this morning. They have done a terrific set of webinars and all these leading up to these super summer sessions. I can appreciate that. I'd like to start out by just saying there's really been a very purpose-driven initiatives by Federal Highways for many years. I am a fortunate person to have been part of every one of these, as the check boxes are things I participated in clear back into 1998. So Ben and Silas and Derek and Mary are taking things forward. And the good part for my presentation today is I can take much of my information when they asked about sharing on methods and things from some of what was done previously. So these materials are available to you through other training materials, webinars, things like that. So it'll be repeatable for some and it'll be brand new for others. The real key is, where are we going? You know, what's the goal here from 2022 going forward? We're talking about a couple of decades of getting to the point to reduce uncertainty in geotechnical investigations. So as I'm going to get into several of the formula and how we get there, no, I can't do that in 20 minutes. I don't intend to, but we do know that the physics is there. We do know that it hasn't changed. What's changed are three things that I'd like to just have you aware of. Our hardware's gotten better, our software's gotten better, but the key is our digital recording and our digital visualization and presentation of results for you, the designer, to incorporate geophysical results into all of your programs, whether it's ArcGIS or any other 3D CAD, things like that. All the programs that are out there, we can give you data to put into it. I think those are the biggest changes, not the physics. So I'm going to spend just a little bit of time on a statistical perspective and some corollaries, and then I'll get into those methods. I'm going to tie those methods into what we know as uncertainty as geophysicists, and then I'll have some applications to sort of back up those methods. Because in reality, you know, we start on a site, and this is just hypothetical as it gets. And in this case, it's, you know, a quarter square mile there, and we're just putting in a 50-foot anything. It could be an old river channel. It could be a dike. It could be a fracture in bedrock or a shear zone or faults and things like that. And if we assume that site and we want to say, all right, it's a narrow target, how are we going to find it? Well, we drill. I know that, or we get cones, or we get any other excavation intrusive methods. And the probability of finding it is very low from the get-go if all we're doing is just drilling and poking and hoping, as I like to refer to it. And we up the number of borings, you know, okay, we up the chance of hitting it. Now we're at 50-50. And that's usually not good enough for constructability and or design. We start throwing more borings at it, and okay, we're getting pretty close of at least hitting it and understanding it might be there. But then at some point, yeah, we know we're going to get this. So, you know, we're going to drill enough holes and pepper the site. We're going to have enough intrusive investigations. But at this point, it kind of turns into this old corollary that we've all seen, you know, that the classic blind man and the elephant problem. Everybody touches a different piece and sees a different problem. And I think that's where geophysics can help best, because it takes this and says, why can't we use these technologies that have existed for decades? I've built my career on it. We know they work. And what we can do is extend what each person in this little cartoon felt and take all of that information and start going into what's unknown and create something more known. And by doing so, we reduce the risk. It was just putting this together. I noticed the eyes on that elephant, like, really? Come on, let's get it right, guys. And so here's geophysics. Some of you, many of you, I know over my whole career, I've heard it called a number of different things. I do want everybody to know a lot of our boxes aren't black anymore. We use yellow and orange and things like that. So, but we do have instruments, and we do sampling with systems. In this case, a couple of geophones pointed out here in the middle. I was asked on a project site last year by a client saying, so how's a geophone work? And I said, hey, that's out of scope. We can't go there. No, I was teasing. And I explained a little bit about it. And we don't do that today. We don't do that with you, but we know how the physics of these things can come in so that when we analyze the Earth, that we know what we're doing is an indirect measurement. I'm not touching it. I'm sampling it with various physics. And those methods of measurement are going to give me properties of the subsurface in whatever fashion I choose, this one being an example of seismic. I got to go back to the old corollary in the medical field because both they have jokes about things. And if you can't read the joke on this, is your x-ray showed a broken rib, but we fixed it with Photoshop. So I kind of like that one. And from the medical imaging perspective, it's really no different. They have a sampling plan, whether it's biopsies or x-rays. They've got testing, whether it's just tapping your knees or anything else. And then they go to full-fledged imaging and MRIs, PET scans, all those different things that almost everybody on this call will be aware of, either themselves or somebody in the family. And we take it for the faith that the doctors have it. We take it for the faith that the physics of what they're doing works. It isn't any different in the inputs and output, in this case, a 3D scan of a brain there, and the things that they can learn from that, and then decide, what do we do next based on changes, based on anomalies. So the two really are very similar. In fact, the mathematics in the CAT scan, the T up there stands for tomography. And so we use tomography, which is just a mathematical program to get to solutions. So how do we reduce risk? Well, you know, I mean, if you've got a migraine, you might say, hey, doc, do I need a full-fledged MRI? We don't know. Well, you go to a site, you say, I don't know, do I need geophysics? I'm in karst terrain, and what might be there? Well, the short answer is maybe not. But if this happens to be the natural ground surface in a nice flat part of the country, and we say, hey, there is subsurface karst here, we don't know what it looks like. It tends to make a little difference when somebody comes up and says, hey, my constructible grade is at this elevation. And so we have to understand it better before we get out there, because you can look at that and say, drill here, drill there. What am I going to do? So the question isn't, do I need geophysics? It's, should you use geophysics in these kind of environments? Geohazards of any kind. This is just one example of karst. And my short answer is, well, you don't have to. If you're like me, one of my geophysicists here that's got the force, and using those geophysical goggles, I'm trying to use a pun here and joke with people I can't see smiling, but these are HoloLens, and we are developing with several companies the ability to take our data and get into the models, get into the subsurface, as I like to put it, and see our data. And so here's the opportunity to use those technologies. So why are these so different? We've seen medical, we've used it for a long time. And geophysics has been used a long time, but it's being implemented more from various agencies, not just federal highways and the state DOTs, those of you that are joining us today. So I like these 4 bullet items for each of those. Why are they so different? Well, the first on the left is obvious. It's got full 3D coverage. That MRI is going all the way around your hip, knee, head, whatever it is you're looking at. And they have a terrific starting model, right? I mean, to most of us, we kind of got the same shape, size, and head and what's inside of it, and zillions of examples. And they got really quick time differencing. They can do that imaging over and over again in a repeat short time frame. Well, we don't get 3D coverage. I'm lucky if I get a borehole to put sensors in, or an adit, or a shaft, or anything else under the ground. I'm typically just dealing with the surface. And even as a geophysicist, when I say 3D, often it isn't 3D like you might think a CAT scan might be. And I hardly ever have a really good starting model. I say it's a rough, because that's why we're being brought in, a borehole here or there, or maybe not yet. They're going to use them afterwards. And every site is different. Let's just admit that. And that Mother Nature, yeah, she can be pretty tough on us on those changes in site conditions. And those can change even during construction. Just moisture comes to mind, or flooding, those kind of things that can be it. So the real piece is that when they're used properly, and you incorporate other test results, remember the doctors do too, then you can start to take these, incorporate them, reduce the uncertainty in your own model, and that will help the geotechnical folks and every designer and project manager just reduce that uncertainty on your site and the risk for your project. So the geodata, and geophysics being one of those, is really where it all kind of can come together. We take anything that's given to us on a site, incorporate it into our data so we can understand what those colors mean. This is a seismic section out in Iowa, and the blue is the Luss Hills of Iowa. But we don't know that unless we just do some geology or use those. To me, the CPT, monitoring drilling, the borings, all of those information are so important that this is what A-GaME is helping us understand. Bringing these technologies, bringing these disciplines together is what's going to help your project delivery and help you reduce the risk during the course of it, but not if we're not using it together. It's probably one of my biggest points for the day. So I was asked to share some methods with you. And in those methods, I picked 3. There are 3 of the A-GaME. A-GaME has several others: electromagnetics, magnetics, and self-potential. And I'm not going to cover those. There's various reasons, some of it just being time. And the other piece is I'm taking materials from before. I want to remind you of that. So if you want some of these, not only is this talk and the slides available, but the background of more. I did a full webinar on just seismic methods, and I think Rob did one on resistivity, or his counterpart Jeff. So these things are available to you in greater detail than we can possibly cover this morning. So seismic, I've got a couple slides of basic concepts. We're measuring all the vibrations going on the ground. We can do that passively by setting out systems and just listen to what I refer to as planes, trains, buses, and cars. The ground is shaking. Oh, by the way, there's earthquakes and microtremors. But we do that with sensors. We can do it in linear arrays or grids. But we're coming out with a color-coded section like the one on the bottom that happens to have found a karst hole in Missouri before they built a dam. Just an example from a previous project. And these are good because they just give you, if you're not aware of the phenomenon of an elastic wave traveling through the Earth and the wave fields that it creates, there's two types: body waves that travel into the Earth and surface waves that travel along the surface. It's not too hard to follow that intuition. Compressional waves travel the fastest, shear waves travel the next speed, surface waves are the latter. And Raleian surface waves travel at the same speed. They just move the ground different, one in a vertical sense, one in a lateral sense. We know these, we know the physics, and using these are how we can go out, design a survey, use the right sensors, use the right array, and get the best answers. Well, the reason any of these work, I will have one of these slides for each method, is if there isn't a contrast in Earth materials, we can't map it. You know, a hard rock on a hard rock, a dense soil on a stiff clay, you know, those kind of things that, you know, as geotechnical engineers, we can't see those contrasts and interfaces if they don't have a change. In this case, going from, you know, the really loose, I'll even use the word crappy landfill stuff all the way up to steel. And these are materials, these graphs come out of the original training for federal highways. So we've got P and S waves, which is the typical for seismic, and we've got the same scale except for the velocity scale. Notice they do travel at different speeds, but for the same Earth materials, do notice that there is no one for water, as there is a very narrow band for water. We know how seismic waves travel through speed. Ask any mariner that's doing pinging for other submarines. And so we can use this to start saying what kind of Earth materials and what sort of range of materials, velocities we might expect. On the GPR side, basic concepts, and this is an old slide again, there are new systems, there's 3D systems, there's lane-wide systems. I just wanted you to get an example of what can be done at highway speeds when we're looking for rebar and cracks in concrete, when we're looking very deep, these systems, this low-frequency system. A colleague of mine in Boston went to 130 feet last week with one of these. These are also geologic mapping tools. And these can be really well used for utilities. So there's a variety of them, but they all transmit an EM wave, goes through the Earth and comes back, goes through the Earth at a variety of speeds. So this again being just a cartoon to show you when we walk along the ground and have GPS there so we know where we are and we get reflections off of features, in this case a utility, we can map where that is. We can also map geological area, whether that's strata or some karst features. So these GPR technologies are very good. You've got to know some limitations for them because a result like this is what you get. It's called a line scan. Seeing interpreted pipes here, the bottom of a concrete slab near a swimming pool, where drains are, all those features, and having the geophysicists pick them out for you. It too has contrast. They're in dielectric constant. Not something most people are familiar with, but we have it basically set for extremes from a 1 in air to 88 in water, and Earth materials are all in between. The best way to look at this is from good materials to use radar in to bad materials. I've used the phrase, I've been wrong because the clay is not a clay, is that clay is the death of radar. It's pretty close to being an accurate statement. And we know this because the NRCS has mapped the entire US. If you haven't seen this map and just get after the suitability, will GPR work where I live and for my kind of projects? Well, you know, it's gone from very good or very high to low. I kind of went the same scale of where it's good to bad. My state has a little mix along the river bottoms, you know, in Nebraska, obviously, got some great sections, northeast, northwest, southeast, terrific areas for the use of radar, but a lot of it is not, and you just have to know that before you pack it up. So what I decided to do is to use a project that was run by Central Federal Lands here out of Colorado. And in Hawaii, after an earthquake, they noticed some distress on the roads, some holes that had opened, and they needed to quickly get after a fix. Also, all my presentations, before I forget, this was given at the Southwest Geotech Conference. These full site case histories can be shown to you later. So here we go. I've got a project with two methods, seismic and GPR. So one project, I'll kill two birds with methods, just kind of showing how they work. Because we had to deploy quick, we had to find lava tubes, we had to do volumetric, and we had to be cost effective because the smaller, oh, wait a minute, that worked for both of the methods. So we went out to 5 different areas. had to be collected in 2 different days, small areas with very concerned pieces to work in. We could only close 1 lane at a time because of tourists. And we were looking real shallow in most cases and trying to define extensive problems underneath the surface. I'll go back one here. This is an example of one of those 3D radar units, obviously GPS in here and an array of geophones laid out in a 3D grid. So the seismic results, unlike the cake show where I tell you what we're going to do and then you get to eat the cake in about 5 minutes. This is the 3D volumetric assessment of these at area 2. And this is an anomaly. And it's going quite deep, about 55 to 70 feet deep, depending on how you look at this and how you smooth it. I'm in cross section here. I'm looking straight up the road here, looking down on the surface here. And the top 5 feet, geophysics isn't real good in that, so it's not a problem for seismic. And this is a file that I can provide for you as well, Ben and everyone else. The GPR, it works a little different where we can take that 3D volume and slice it in depth. So I'm going to give 3 depth slices. We're 1.2 feet below the surface, not much going on except a little crack or something going on here in the center, which by the time we get down to 2.5 feet is opened up into an air-filled void. And then about 5 to 7 feet, we started losing any trace of it, but we could tell it took off in this direction. So in the end, using the GPR in the shallow and the seismic for the deep showed that this was where that void was, right on the shoulder at the white line, open and could stick a tape in 25 feet, extended much deeper and extended all the way across the roadway. So the results here were useful for Central Federal to be able to move quickly to get something done. And my former friend Camise that worked on this said that they worked on this project quickly to get something done in less than 30 days from when these distress features showed up. They didn't drill it. They used the geophysics to make a design and get this thing back open and safe for the public. One more quick example of seismic, and I'm going to be running out of time here. I see Ben, I'll go quickly. This is a recent project in March with snow there on the side of the road along I-70, just west of where I work. And the idea is for a wildlife overpass. And so a bridge is going to be built and borings were done, but the borings were pre-designed, so they weren't sure where the foundation elements might be. So we did some seismic. Here passive was we had trucks and we had a front end loader thumping the ground. So we used shear waves to show that maybe if you're using just refusal and blow counts, probably not much different if you're going to be able to found your elements in that outside of where the existing borings are. And this quote, between, below, and beyond, comes from where Ben works in the southeast center there from a gentleman named Barry Berkovitz. And I've loved that phrase forever, between, below, and beyond boreholes. This is an example of that. If they have to rock socket into hard confident materials, there's a pretty big difference in elevation for where we would have this element and where we'd have to take this element. You don't know that going in. That's a cost of the project. Resistivity, I'm sorry, I'm going to run over time here a little bit, Ben. I want a good example. We inject current with a couple of electrodes, and we receive with a couple of other electrodes called voltage potential. Then we can map features in the ground using systems on the earth that can cover miles a day in some circumstances. But they all have a contrast in earth materials, or this wouldn't work. For those of you that are used to resistivity, the inverse of that is conductivity. So we have changes in material contrasts. That is why it works. So this is a project that I presented HGS many years ago, looking for karst in Oklahoma on Highway US 412, and it's separated by 2 counties. We were looking for these zones of gypsum dissolution, and it was being done. There's my timer going off, telling me I should be done, and I'm not. So that we could find how they could take a 2-lane road into 2 separate 4-lane passes. Benign surface, doesn't look bad at all. The subsurface is not benign. Red are features and problems of concern. We did 8 miles like this, and we did both right-of-ways. So this is all parallel to each other. There's the road to be constructed. And we were able to work in the medians and proposed lane alignments, and looked at where they were going to drill ahead of time, and they did encounter a void, so they did drilling after the geophysics. and also just some of the field observations. We knew when we were out there that it was hollow underneath, and this is an area with the Tonga caves and some well-known pieces that have endangered bats. So the key for us was to get this data, go through some geophysical pieces of statistical analysis with the geotechnical information, come back with a more easy solution to utilize and understand. The color scale on the right, we redid our maps with basically 3 colors. Green is good, red is bad, purple is we're not sure. And now the constructors could get in there and look at long sections of this roadway, and many of them were green. They were good. There weren't going to be problems. But you've got problems when you start working in environments like this and lateral changes in the dissolution. So my last couple of slides here, this is where I think the A-GaME is going. And this is an active initiative by the Corps of Engineers to kind of say, we've been using geophysics over here in all of this part for a long time. Maybe we ought to think about bringing it up earlier into the process. Environmental did this in the 90s, right? It was over here as well. When you hit something or a wetlands, you kind of dealt with it during that project. Now you can deal with it earlier on in the programming charrette or early in the planning reports. And I think that's a real key, and it's a good tie to what the A-GaME is doing right now. Lastly, I just say, hey, you've got to work within a budget, but I think we all have to plan as if unknown conditions might exist, as the owner at this site where a dam was built thought they might exist. So sure, geophysics should be used. I'm a contractor, so I would always say that, right? But large areas, if you need continuous information, you only have a few borings, and you've got to optimize where to drill further or other things and reduce uncertainty. You know, these have to be used when you're in rugged terrain, wetlands, and environmentally sensitive. So there's a reason I say yes, use geophysics, but I believe the reason is really to reduce your uncertainty and lower the risk to project scope, cost, and time. So I'm sorry I'm a couple minutes over there, Ben and crew that's following me, but I do appreciate the opportunity to share today. I hope I hit the notes for a few of you that make this understandable and usable on your projects.
Very good. Thank you so much, Phil. Great presentation, great overview of the geophysical surface methods. Yeah, and we will be talking a little bit more about how those applications can help us with specific problems when we get, you know, in the construction realm. Right now, I will turn it over, allow Gerald to get ready here while I introduce Gerald Verbeek. Gerald Verbeek is with Royal Geotechnical North America. Gerald has spent about 20 years in the oil and gas industry before starting a management consulting business in 2004. One of the activities of his firm is helping European companies and with their business in North America. And as part of that, he has been active in promoting soil and foundation testing philosophies and equipment. In the area of soil testing, he works with Royal Geotechnical, where he serves as the technical advisor for CPT. Gerald is active in various organizations, including the U.S. Academy of Science, Transportation Research Board, and ASTM. He also is the chair of the Geoindustry CPT Users Group for the United States of America. So with that, Gerald, you have the floor, sir.
Thanks, Ben, and welcome everybody. First of all, just to help Ben out a little bit, the name of the company that I work with and do all the CPT work with is Royal A-GaME, a Dutch company that has been involved with CPT for quite some time. The session title today is, as Ben told you earlier, is Manage Risk, Reduce Geotechnical Uncertainties Before Construction with CPT. And when I thought about it, it was kind of like, well, yeah, that's fine, but we really should talk about before and during construction, because the target audience, as Ben told me, are project managers, are construction managers. And what I really would like to do is focus on that audience to see how we can utilize CPT penetration testing to the benefit of all the people that are on a job site, and also address the problems that you have during construction, not only before construction. As usual, when I make a presentation about CPT, I have a couple of disclaimers. I'm a Dutchman. I was born and raised in the Netherlands, got educated there, and that basically means that I am a conehead. To explain to you a little bit where it's coming from, here in the United States, when you go to an engineering school, when you are talking about soil investigations, the main emphasis will be on SPT. In Holland, from the very beginning, it is cone penetration testing. Not surprising, because cone penetration testing was developed in the Netherlands in the 1930s, but that also makes you understand why I strongly believe in cone penetration testing. At the same time, as always, and you'll notice that a couple of places during my presentation, I will try not to be biased. I will try to give you some honest assessment of what CPT can and what it cannot do. Because I think the most important thing is, as Phil was alluding to as well, is we need to know what the methods can do. And only if you know the weakness of the methods that you're applying, can you make optimal use of those methods. Maybe not all of you are familiar with CPT, and that's why I put in this slide. If you just focus on the graph on the right-hand side, you see there a truck. It could be a crawler, it could be a trailer that has a pusher on it, but it's some kind of a carrier that brings a pusher to the job site, and that pusher, hydraulic pusher, is pushing a cone into the ground at a constant speed of 0.8 inches per second. And that cone, as you can see, enlarged in the middle of that graph, measures the tip resistance, the pore pressure, and the sleeve friction. In other words, you have three measurements that you get as you are moving down through the soil, and those measurements are recorded every centimeter, every 0.4 of an inch, which basically means that you get a continuous profile until you reach either your target depth, if you're being told to go to a certain depth, or when you hit refusal, when you simply no longer have enough pushing capacity to go through the soil any further. What's important here is that everything in this process is heavily standardized. And you see the reference to the ASTM standard, but whether you use the ISO standard or the ASTM standard around the world, we're using the same speed, which will move the cone down, and basically the same dimensions of the cone. It's very heavily standardized. The shape of the tip, the length of the sleeve, everything is standardized. And that's important. Why? This electric cone has been utilized basically unchanged since the early 1970s, so about 50 years. And since then, we have done billions and billions and billions of data points. And those have all been put together and have validated this procedure. So therefore, we know pretty much what's happening. It is something that is simply there. We know what is going on. What do you get then when you push that cone in the ground? Are these three graphs on the left, again, a schematic of the cone. You see the tip, the QT to the bottom, the pore pressure generally taken right behind the cone tip, the U2 in that case, and then you have your sleeve friction. And you get, as what you see there, the remainder of the screen, three continuous profiles. Paul Main at Georgia Tech, or previously Georgia Tech is now retired, used to refer to those lines as squiggly lines. You see every single detail, not a data point every foot or every 3 feet or every 5 feet. No, every centimeter, every 0.4 of an inch, you get a data point, and that means that you can really catch everything that's going on. As you can see here in the tip resistance between, say, 14 and 16 meters, you have this high tip resistance. You can actually get it. You can notice that. And what do we do with those data points? We basically, since we have three data points, we look at them most of the time, initially at least, in groups of two. The vertical axis, you see here the tip resistance, and on the horizontal axis, on the left-hand side, the friction ratio, which is nothing more than the sleeve friction divided by the tip resistance, and on the right-hand side, a parameter that's derived from the pore pressure reading. And in that graph, we have identified 12 fields. And in those fields, for each of those fields, we can identify how the soil behaves in that area. Not what it is, because we don't take samples. We cannot look down in the soil. We cannot touch the soil, but how it behaves. And that means when you are in section 6 here, you know that you're dealing with something that behaves like a sandy silt to a silty sand. Now, to me, that makes perfect sense. I don't necessarily need to know what the soil is. I want to know how the soil behaves, because when you put a foundation in the ground, that foundation cannot look or feel or touch either. That foundation derives its bearing capacity from the behavior of the soil. So it makes perfect sense that we start looking at how the soil behaves rather than anything else. What's happening in reality is something like this. You come to the job site, you start pushing your cone, and as you're pushing your cone, you get those squiggly lines. Now, in reality, it doesn't go as fast as this. It goes basically for every meter, every 3.5 feet or so. It takes you about a minute, but you get the idea. And it basically means that in a nutshell, you can say that you come to the job site, you start pushing the cone, and before the cone comes back out of the ground again, once the cone is at the deepest point, you basically have to report. You have this on your screen. You can email the data straight to the office, and it means that you have right then and there, not days later, not weeks later, no, right then and there, you have a very good continuous profile of the soil with an indication of how the soil behaves, which you can see here on the right-hand side. Another way of looking at this whole thing is that you get a continuous profile, another reading every couple of feet, and you get 3 parameters, and not just one, as you get with SPT. So we have 3 parameters, and with those 3 parameters, we are able to really characterize the soil pretty well and get a good idea of what the soil is all about, how it behaves. Once again, we don't claim with CPT that we know what the soil is. We're purely saying that with CPT, with all the correlations that are available, we have a good idea how the soil behaves. Now, I told you at the beginning, I was going to be non-biased. So there are some reasons why people claim and why you should not use CPT. And let me just go through a couple of those things. First of all, I still hear quite a bit here in the United States that people say, well, yeah, that's great that CPT is utilized, and you're a Dutchman, in Europe it may be utilized everywhere, but here in North America, it's simply not used in my organization. Fortunately, that is changing. I've been active in the CPT world in the States now since 2006, and over the last 15, 16 years, we definitely have made a lot of progress. So join the club, start using it as well. The other argument that I often hear is, well, my client doesn't accept this method. I would like to use it, Gerald, don't get me wrong. I think it's a great method. You have convinced me, but my client doesn't want me to use it because he doesn't accept it. And I think that is where this A-GaME initiative where it really helps. Although what you see here is that I have changed slightly the title of A-GaME. I don't think necessarily it's an advanced geotechnical method. It's an underutilized method. It should really have been the U-GaME rather than the A-GaME. Now, that's probably as an acronym not as catchy, but these methods have been around for a long time. We know what we're doing, just like what Phil was saying about geophysics. We know what we're doing. Simply, they haven't been utilized all that much, and that's why we really need to make an effort to start utilizing them a lot more and get much more wider use of those things. The argument that I often hear, well, Gerald, it's great. Our soils are not suitable. Phil showed you a graph where ground penetrating radar is suitable in the United States. And here I often hear the soil is simply too hard. Well, what you see on the right-hand side is a little chart, and it gives a relationship between the hardness expressed in the SPT number, the N value, and on the vertical axis, the pushing force. And when you are realizing that most CPT trucks have a capacity of about 20 tons, then you can see there that if you can push a split spoon, you can basically push a cone. Provided, and we have to be fair, there are not too many boulders. You cannot push a cone through a piece of steel. You cannot push a cone through a piece of concrete. That's on landfills with construction debris, that's a problem. You cannot push a cone through boulders. That's absolutely a limitation. And then you still have people that say, well, Gerald, CPT is great, but I need to touch, I need to feel the soil. And I would like to have samples. If you want to do that, we can even do that with CPT, not while you do the sounding yourself. You have to wait, push the cone again, then with a dummy tip, you retract the tip, and you can take a sample up to 2.5 inches in diameter, up to about 3.5 feet long. So if you do need samples, we can achieve that. Let me illustrate now some of those aspects of the benefits of CPT with a case study. And it's not surprising, after all. It started off with this chart saying, if you ain't Dutch, you ain't much. Now it's a Dutch case study from Holland, where they put near Hoofddorp, which is a town just south of Amsterdam Airport, Schiphol Airport. If you've ever been there, you probably flew over that location. Little apartment building, 4 to 5 stories. You see the architectural image on the right. No basement, driven pile foundation, and it's about 160 by 110 square foot. Tiny, small, not even a full city block. Only about a quarter, say, of a city. During the initial product development stage, they did have some CPT soundings that I showed you here on the screen. And I just would like you to focus on the red lines, the tip resistance. And what you see there, they're about 200 feet apart. On the left, the number 1 location, you see a very clear, very strong, very stiff layer, sand layer there, where you could use to put your piles in. Location 2, not really. Nothing was there. So for that reason, they said, okay, apparently in this location, we have site variability. Yeah, let's have a decent amount of CPT. Now, mind you, every of those CPTs will take you roughly about half an hour to perform. But they agreed on doing 22 CPTs. So about 11 hours worth of work, day and a half or so. And the conclusion, unfortunately, was that when you start looking at what I showed you here, that red line, if you take those CPT soundings and you put them side by side, you get something. Oh, I'm going too fast. Let me go back here. Red line, if you put those soundings side by side, you're seeing there that there are lots of question marks who really don't understand how the profile is going. But remember, the data could be sent straight away to an engineering office. You can look at it in real time. And based on that, before the guy demobilized, it was said, nope, we're going to do some more. And in the end, they did another 22 CPTs for a total of 46, which basically means that you did 1 sounding for every 400 square foot. And with that, we really were able to come up with a very good understanding what the soil profile was there. Very detailed analysis, but with the information available pretty much straight away. Because of the analysis, we could then identify that small area, 3 different zones, 3 different areas. Area A, which had a very clear soil layer, and unfortunately, I did not have time to change the colors. Here you see that the tip resistance is in blue, but here you have a clear, thick layer where you can put your piles in. Area C, we have the same thick layer, but it's deeper than in area A. And then we have in area B, an area where you really don't have any layer where you can use end bearing, so it's all going to be friction piles. But we now know at least what we have, therefore we can design the piles and everything is going smoothly. Let's assume that we had not done this extensive site investigation. Let's assume that you did your borings and 3 weeks later you get the results from the lab and it's really not a good time to go back again. What would then be the case? Well, if you had based everything on the location A, of the data was utilized, the data here, then you would have assumed that already at this depth you start having a load-bearing layer. Therefore, most of your piles would have been too short, therefore failure of the foundation. On the other hand, if you had based it on location C, the opposite would occur. Most piles would have been way too long, and therefore you not only over-designed your foundation, but you also had problems with pile installation. And that brings me back to the construction manager. When he has something like that, we'll come to that in a second, what are you going to do then? And if you had a situation that you base it on either A or C, the piles would not have worked in location B, they basically would all have failed there. So it made perfect sense to do more CPT soundings, and because you get the results instantaneously, you can assess on the spot whether you have site variability and then take corrective action if necessary. So we talked about doing CPT during the site investigations. You can utilize your CPT data for foundation design. You don't need to go back to N values. You can use this as a direct input, but in the interest of time, I won't go into that right now. And what you can also do, you can take your CPT data, use it as input into a pile driving simulation program, and you get your blow count. And that basically means that before you go to a job site, the construction manager already knows what blow counts he can expect. And if there's a large deviation, it could be that the hammer is not working properly. Or it could also be that at some point you're going to have a really unexpected event during construction, which is when you design for C. In other words, the load-bearing layer only starts here, but you are in area A, then you start having a much higher blow count around this depth than what was anticipated. And then what do you do? And in that case, my suggestion is always have a CPT truck, a CPT unit on the job site. If you come up with something that's unexpected, you just push con. You don't just look down and ponder and talk about it and have a meeting about it. No, you push a con, and 25 minutes later or so, you have your answer and you know what is going on. Oh, in other words, what is CPT? Well, in my opinion, it's an efficient and exciting soil investigation method that generates a continuous profile that is ideally suitable for all the phases for a project. But quite often I get the response, "Oh, yeah, Gerald, really? I'm not convinced. There are still some things that I think that we need to do slightly differently. I still have some questions." And so what I've done in the last part of this presentation is really go and look at some of those questions and try to address them. First question always comes up. Yeah, CPT, but I'm used to geotechnical boards. How do they work in relationship to geotechnical boards? Well, they're similar in that you get a soil profile, but they're different. Different in the sense that when you do a boring, you get your samples. You might look at them on the job site, but generally speaking, you send them to a lab, you get them tested, and a couple of days or weeks later, you're going to get some results. With CPT, you have the results right then and there, which means that there's also no phased execution. You don't have to send it to somebody else. You don't have somebody else there that supposedly starts to look at, is this a silt or a sandy silt or something like that? No, the correlations that we have immediately tell you how the soil behaves. You have no cuttings, no spoils. And especially in areas where you have contamination, where you have to do all kinds of work to take care of the soil that you bring out of the ground, that may be a tremendous advantage. Disadvantage, you have no samples, at least not at first. If you want to get samples, then you have to push the cone with a dummy tip again and then get a sample at the area where you want. And then if you want to calibrate the CPT soundings, you can do the opposite thing that Phil was talking about earlier. He was talking about the geophysical data that gets calibrated or really linked to a CPT sounding. You can also here take all the CPT soundings and then link those to a single boring so that you get a better idea of what the soil actually is, not necessarily how the soil behaves. So that's the first question. Second question, something that project managers and owners, of course, are very interesting. How can CPT benefit my construction site? Does it pay off? And I think the answer there is yes, and even more so if you are a little smart and start to think about it. Before I set up my management consulting business, I was the vice president of engineering for a large turnkey construction company in the oil and gas industry. And what I always insisted on during the project execution is that there was time for me to go back to the job site after the site plan had been finalized and before we had to do detailed design. And I'll explain to you why. Let's start at the beginning. How can CPT benefit my construction site? It provides much more data. You get a continuous profile, not just a data point every so many feet and then just connect the dots. It provides the data at short notice. You really can get this data in your hands really, really quickly. Can be used to optimize the foundations. If you know your plot plan and you know where your site plan and you know where you have the heavy foundation areas, the heavy loads, then at least you can do some additional sounding there and get data specifically for that location. And then, as I said earlier, if you have questions, problems that arise during construction, you can do additional sounding to know exactly what is happening at the location where you're working, because you can push a cone just adjacent to where you're working. To change my better planning procedure? Yeah, because it provides a better model. It's a continuous profile. It also helps you because you can use the CPT data directly as direct input in your design methods. Quite a few states now have methods where you can utilize your CPT data directly as input for your foundation design, and therefore it really helps you. And as I said earlier, it can help you to optimize the foundation if you can do some work, if the schedule allows it to do some additional investigations once your site plan is finalized. Should it be done? Well, obviously, at the very beginning, during detailed design, once the plot plan has been finalized, and during construction, which means in all phases, not just during the soil investigation part of the project. No, in all phases does CPT make sense. Does it impact construction activities? Not really. Yes, you need to be out of the way because the truck that will be there takes some room. But other than that, it's really not necessary to do anything differently. You can continue on with your soil investigation, your construction activities, whatever is happening. Only when you perform seismic CPT, where you put a seismic sensor behind the cone, then it may be necessary to stop briefly some activities. But basically, you can do whatever you need to be. You can continue with your activities. And I see I should have removed that last sentence there. I apologize for that. Safety aspects. Well, the biggest thing is you generally speaking have a large 20-ton truck, so you need to figure out how to move it to the various test locations. You need to pay attention when it does move. You need to have a suitable working platform. The most important thing is you need to know where the underground services are. Because while CPT tells you what is underground, we need to make sure that we don't hit a water line, which creates fountain. Not all that bad, but not much the thing that you want to do. An electric cable, a little bit bigger problem. And then the worst part, of course, is when you hit a gas line, because then you can get an explosion. So always know what the underground services are. And then, of course, when you are in a contaminated site, when your cone comes out of the ground, it may be contaminated as well. So you need to pay attention to those hazards. Finally, can we perform CPT in-house, or should we get an outside contractor? Oh, no, you can do it in-house. It's a very standardized process, and that's the beauty. Anybody can do it because there are very few things that you can alter. It tells you what size cone to use. It tells you how to push it into the ground. It tells you what to do before and after sounding with calibration. Everything is finalized. It does require a capital investment. But what you then can do is, instead of getting a full 20-ton truck that can do all your CPT work, you can go in small and make sure that you have something available that can do most of the work. So those are most of the major questions. And I hope with that, I have at least some of those people that were reluctant and convinced that it's an efficient and exciting soil investigation method that generates data that's essential for smooth operations on a construction site. And in the last minute, Ben, because I have still one more minute, I do want to say a little thing about the CPT users group. Ben already alluded to that, but Phil should have done the same thing. Federal Highway initiated some geo-industry CPT users group, or users groups, I should say. Phil is chairing the one on geophysics. I'm chairing the one on CPT. We meet monthly. The last Tuesday of each month, we talk about CPT at 3 p.m. Eastern time. Please feel free to join there. You may become a cone at yourself. That's the risk. Hopefully you get enthusiastic about CPT, and that's hopefully with this presentation, I've achieved at least some of that as well. With that, thank you very much. And if you have any more questions, either late this afternoon or please feel free to contact me at any time.
Thank you so much, Gerald. Great presentation. And sorry for butchering your company's name. I will learn better. But thank you so much. And there is a question in the chat pod that came in specifically on CPT, and I think it's worth asking at this point. But the person posed a question. You know, we have a bridge replacement project over a river with water depth of about 100 feet and sound material about 250 feet deep.
Yeah.
Is it feasible to perform CPT testing under these conditions, and will there be any issues with rods buckling?
Yeah. If you do CPT the standard way, there is going to be a problem because let's face it, if you start going to that depth, you probably have to push with 20 tons. And if you have 20 tons sitting on a rod that has a diameter of 1.44 inches, that is going to buckle. So whenever you are doing CPT in soil that does not give lateral support, or in this case with water that doesn't give lateral support, you go down with your cone until you start getting somewhat of a resistance, so the cone doesn't drop anymore by itself. Then you stop. Then you put casing around the CPT string. Normally, the rods have a diameter of 1.44 inches or 36 millimeters. The CPT, the casing, has an OD or of an ID of the opening of 38 millimeters, so slightly bigger. You put it over your CPT rods, and then you go further down, and that way you won't have any buckling. But you do need to have casing, and if you have a lot of flow in the river, you might even put a standpipe around your casing so that you don't get bending in your casing, which then could affect a problem later on as well. So you need to do something with that, but it is not really that big a problem, and you can definitely do it. And if they want to get more information, please feel free to contact me.
Great. Thank you so much, Gerald. Our next speaker, and as Mike Rodgers gets ramped up here, I will introduce Mike, but I also want to remind everybody, because we did have a question in the chat, keep them coming, those questions. And if you have comments, please feel free to put those in chat. We'll be monitoring those. And if you have something for us for discussion later on, please put those in there and we'll get to them. Our next presenter is Mike Rodgers. Mike is with the University of Florida. He is a research assistant scientist in the Engineering School of Sustainable Infrastructure and Environment with the University of Florida. His research has been focused on developing new methods to improve geotechnical site characterization and full-scale construction monitoring. Measurement while drilling is his topic today, and he got his PhD on this topic and has been pioneering this application for geotechnical engineering for the past decade. Mike, please take the floor.
Thanks, Ben. And I'm going to go ahead and kill my video here to save some bandwidth. But as Ben discussed, I'm going to be talking about measuring while drilling, both from the site investigation side as well as the construction side. Again, we want to reduce risk and reduce uncertainty. So we're trying to show you how we've done this in Florida. So some of the geotechnical design challenges that we face in Florida, our bored piles that support our larger structures often rely on a competent length of rock socket to develop the necessary axial capacity to satisfy the engineering design. However, as described by A-GaME et al., the subsurface stratigraphy of Florida sites underlain by weathered limestone formations can be highly variable with respect to material layer thickness and strengths, even over very short horizontal distances. And these conditions present a challenging environment for the design of drilled foundations in terms of axial performance. And A-GaME et al. Identified a few of the following contributing factors to this. He said that due to the variability in subsurface conditions, it's not always possible to anticipate the stratigraphy based on borings, even when we're a short distance away, and sometimes even across the footprints of a single foundation unit. And the highly weathered material is not well suited for typical investigation methods designed for soil and rock. So we're talking about SPT borings, CPT soundings, and traditional rock coring. They stated that none of these tests are fully capable of defining the in situ strengths for design in weathered limestone, and it's a challenge to assign material properties to a seemingly erratic stratigraphy that will produce a meaningful correlation to load test data. And so this is why the FDOT has turned to MWD to improve our geotechnical design, get a better understanding of our subsurface conditions, as well as board pile construction QA/QC. So if you're not familiar with measuring while drilling, this is the application of monitoring and recording drilling data during the drilling process. It's conducted using computerized systems with sensors placed on the drill rig to monitor a series of parameters. And this monitored data is often displayed in real time and then recorded for further analysis. And similar to CPT, this continuous sampling produces high resolution profiles on a centimeter scale of individual and compound drilling parameters that we can use to quantify changes in subsurface conditions, assess geomechanical properties, as well as optimize our drilling operations. And as you see on the right-hand side, MWD can be used to increase and improve the data collected during site investigation for geotechnical design, and as a QA/QC tool during board pile construction. So on the top right, we're performing MWD on the back of an SPT rig. And on the bottom picture here, this is a typical drilled shaft rig, and we're installing a drilled shaft, and I'm monitoring this installation from a safe distance away. And both of these applications produce a significant amount of data that can be used to address the problems that were described by Graham et al. Here in Florida. So first, I'm going to start with the site investigation side and first focus on MWD-assisted rock coring in Florida. So due to these challenges that we discussed, low recoveries and poor rock quality are pretty common here in Florida. And in many cases, we collect an insufficient amount of data during the site investigation phase to properly characterize the site for geotechnical design. However, from our recent findings with MWD, they indicate that these low recoveries and poor rock quality may be attributable to our coring techniques that we're implementing rather than the in situ conditions of Florida limestone. And MWD provided an ideal solution to quantify the effects of our drilling techniques on recovery and RQD, as well as a mechanism to provide an increase in the number of strength assessments and data gathered within a rock mass to improve the characterizations. So one of the biggest findings that we came about during our initial study is that in rock coring, there's 3 possible phases of operation that exist. And Tournay et al. Actually found the same thing for drag bits for oil and gas drilling. And these phases are phase 1, which is the inefficient phase. Phase 2 is the optimized phase. And phase 3 is the destructive phase. And from our research, we feel that in most cases, we're probably actually operating in phase 3 and compromising our samples prior to laboratory testing, which is going to give us a mischaracterization on the sites and lead to overly conservative design. And what we also found is that in order to optimize drilling operations, our core recoveries and RQD, is that phase 2 must be maintained throughout the coring process. Now with conventional coring, when we're not using MWD, maintaining this optimized phase can be quite challenging. However, with MWD, we can develop drilling guidelines and procedures to ensure that we're only using our drilling tools in the most efficient manner, staying in that phase 2. And when we do this, the characterization is reflective of the strata encountered, and it's not influenced by our drilling techniques. And a significant benefit to this is that we can reliably assess rock strength in situ during the drilling with high resolution. So 1 or 2 centimeter scale is what we're talking about. However, in order to measure rock strength in situ and to optimize our recoveries and RQD, certain drilling principles must be understood and followed. And we call these the operational limits of the drilling tool. So through our studies, what we found is that interdependent relationships exist between each of these drilling parameters, and these relationships must be considered to achieve the most efficient drilling practices. And so this introduced a new concept of operating within optimal drilling parameter ranges based on these interdependent relationships that happen to be unique to the geometry of our drilling tool. So using MWD, these optimal parameter ranges can be identified for each one of our drilling tools that we use out on a site, and they can be maintained through MWD throughout the drilling process. And when we do this, we get exceptional results. And on the right-hand side, this is a great example of this. So for the particular core bit that we're using, we determined these optimal parameter ranges. And during this core run, we maintained these optimal parameter ranges. So basically we set we set our control drilling parameters within the optimal ranges, and then we didn't change a single thing throughout this core run. We didn't have to make any adjustments to our controlled parameters. And as you can see, we transitioned through rock that was over 6,000 PSI into soft porous limestone that was less than 200 PSI. Again, without changing a single thing, but we recovered every bit of rock that was there, and we're getting proper characterization. Additionally, once we understand these operational limits of phase 2 for our drilling tools, we can develop correlation between specific energy, which is a compound drilling parameter, which is displayed on the right-hand side, top right. And basically, we can relate this to rock strength. And so now what we're doing is we're relating drilling parameters to engineering parameters that we commonly use in design. And this is what allows in situ rock strength assessment. So if we look here on the bottom right-hand side, we have a plot where we have specific energy recorded from MWD. And in the y-axis, we have unconfined compressive strength from laboratory testing, the core samples that we recovered. And so what we see here is data grouped by combinations of variable flow rates and rotational speeds. And these were within the optimum ranges. You'll also notice that there's different clusters of data. This is because this was conducted in controlled limestone, or a synthetic limestone, where we were controlling the strength. So we did different strengths over basically the full range that we anticipate in Florida, or the range that we're most likely going to encounter. So we have 10 different combinations of variable parameters that we're throwing at it. We have 85 different core runs that are considered here. And basically what we did first for this core bit was we determined the optimum rotational speed. And then this optimum rotational speed dictated the penetration rate that we could use to achieve an efficient penetration per rotation range that was identified for phase 2. So now that we know this efficient penetration per rotational speed range, our flow rate then dictated how much torque and crowd could be applied while maintaining this efficient U to N range. And as long as we stayed within these optimal parameter ranges, we had excellent correlation here. And the other benefit was that our recovery in our RQD was 100% for a QU range of 180 to 2,800 PSI in our controlled laboratory. And this accounts for about 80% of the rock strengths in Florida based on historical FDOT data. And what's great about this regression curve here and the equation that comes from it is that when we're out actually in natural Florida limestone, we can use this equation to assess rock strength in situ as long as we're maintaining these operational limits. So basically, as we're coring down, we would get a value of, let's say, 100,000 kPa. It goes up and hits the curve, and we can estimate that that data point is about 9,000 kPa for unconfined compressive strength. And this is an example from natural Florida limestone. In Perry, Florida, where we're using a double wall core barrel with the same core bit we used in our controlled study. And what MWD did was produce a continuous high strength or high resolution strength profile to identify layering at each one of these borings. And in the middle here, we can see boring 5, the strength profile from boring 5. So in the blue is MWD. This is the unconfined compressive strength measured from MWD. And then the orange dots are the core samples that we sent back to the lab that were tested in the lab. So for this one single boring, we had a dry unit weight range that ranged from 100 to 165 PCF. We had a moisture content range that ranged from 0.7 to over 20%, and an unconfined compressive strength range that from 66 to 6,300 PSI. So basically, we encountered the entire range that we expect to see in Florida in this one single boring, where we had a mean recovery of 92% and mean RQD of 75%. If you're familiar with Florida coring, this is very unheard of to achieve these types of mean values over the entire boring length. And so what we did, what MWD did was optimize the recoveries and ensured RQD was reflective of the strata encountered. And in fact, our lab technician commented that he had never seen so many competent rock samples sent back to the lab from the site. And also what we did at this site was we sent out one of our other drilling crews from a different district. He was a very well-experienced driller. He's actually taught me quite a lot about rock coring and geotechnical drilling. And we had them go out and perform rock coring without MWD. And our MWD efforts more than doubled the number of testable samples collected per linear foot than conventional rock coring at the same site. So it's me who's not a very experienced driller. I'm experienced with MWD compared to a driller that has 30 years of experience. And we more than doubled the number of testable samples sent back to the lab. And we also recovered far more low strength rock. And if we look at the far right-hand side, we can see that the lab core statistics and the MWD statistics are in very good agreement. We have very similar average values here. We're seeing very similar variability. This is the coefficient of variability, the CB. And if we look at the cumulative frequency distribution, we see that the strength distribution is also in agreement over the entire strength range. So we have excellent agreement between our in situ assessment and our laboratory assessment. But what we notice from MWD is that we have a significant number of data points that were collected. It's more than an order of magnitude than the LabCorp samples that we were able to collect. And basically what MWD was doing was filling in the gaps where we were unable to collect testable samples. And so this greatly improves the information available for design. And it also increases confidence in the data that we're using for design, because the in situ assessment from MWD and the laboratory assessment from the testing were both in excellent agreement. So again, we're building confidence for a highly variable site. You can see there was a significant amount of layering here. So we talked about the positives of MWD. I want to show you some of the negatives that can occur and what happens when you're in phase 3 drilling. So again, this is in our controlled environment with synthetic limestone. So we should have been able to recover this material at 100% recovery and 100% RQD. It's all competent. So what we see on the left-hand side, there's a picture here. This is from phase 2 drilling, where we're maintaining our operational limits. And then for phase 3, there's actually 2 loading paths. There's stall here. And what happens in stall is basically you reach a certain point and your drilling begins to stall out. So we can see, compared to the operational limits, we're penetrating at a lower rate, and our rotational speed, or our penetration per rotational speed, is actually dropped off, even though we're applying a significantly more crowd and torque here. It's about 5 times the amount of torque and crowd, but however, we're drilling slower. Now we can overcome this load path of phase 3 by just applying a lot more crowd, and we can improve the penetration rate. So that's what we did here. We can see that we've improved the penetration rate and the penetration per rotation here by just applying a lot more torque and crowd. But all of this additional torque and crowd beyond the operational limits, basically what is necessary to efficiently cut this rock, leads to generating wasted energy. So if we look down here for specific energy, we see in the phase 3, we have more than 7 times the amount of specific energy that was going into this rock. And all of this additional energy is damaging our core specimens, and it's also preventing in situ strength assessment via MWD. So we can see when we were following our operational limits, we had excellent agreement between the core strengths and the MWD strengths. It was less than 3% difference. And we also produced 10 testable samples, was the maximum amount of samples that we could have produced here. But for these phase 3 core runs, they both produced 0 testable samples, and MWD greatly overestimated the material. We've also given this fresh synthetic limestone a very weathered appearance. So we would have completely mischaracterized this rock had we not been following the operational limits of MWD. So MWD can be expanded beyond core bits. We can also do this with bits like tricone roller bits, BDC bits, drag bits, things like this. And we can develop operational limits for each one of these unique bit types. And so that's what we're presenting here. We have a tricone roller bit, we have a step profile core bit, and we have a crown profile core bit. And what we notice right away is that each one of these drilling tools has a unique bit geometry. And so what I'm talking about is the shape of the cutting face, as well as the size of the cutting teeth in comparison to the size of the cutting face. And what this does is this dictates our optimum penetration per rotational speed range. And because each one of these has a different or a unique geometry, this produces a unique mechanical efficiency for each one of these drilling tools in excavating materials. And this unique mechanical efficiency based on the bit geometry produces a unique relationship between specific energy and rock strength. So that's what we're seeing here. We can see that the tricone roller bit has much larger teeth in relation to the size of the cutting face, and we're actually able to break out much larger rock particles and flush them out. And so this is more efficient drilling, and we see that this requires less specific energy than the core bits to drill out the same strength rock. And then we can see for the step profile bit has larger cutting teeth. That's indicated here by the SPC value. So the lower the SPC, the larger the cutting teeth compared to the crown profile bit. And this allows us to break out larger rock particles with the step profile bit, and this is a more efficient drilling tool. And again, it generates a different relationship between drilling parameters and engineering parameters. But once you understand these operational limits, it's easy to do this for each one of our drilling tools. And so this is very important that we were able to develop this for tricone roller bits, because these are the types of bits tricone roller bits, PDC bits, drag bits, things like this are what we're going to use for MWD in situ soil assessment. And so we did a brief study a while ago with the tricone bit, where we completed a 25-foot boring in under 10 minutes with minimal effort. And what we see here is this specific energy profile in the middle, and it's normalized, so don't worry about that right now. You're not going to actually get any specific energy values, but it's just normalized specific energy. And so what we see here is that MWD indicated very low specific energy and cohesion with soil with low SBT flow counts, as we see here on the right. So this is an A3 soil right here. And then as we transition into an A24 soil, MWD indicated increased specific energy in this cohesive material with higher SBT flow counts. And what we also see with MWD is, because we're recording flow rates and injection pressures as well, we're actually recording 6 parameters during this drilling. We see that the injection pressure increased in this lower permeable soil. And we were able to confirm that with comparative vertical in situ permeameter tests, where in the loose A3 soil, we had much higher permeability. And when we got into this cohesive material, the permeability actually dropped off by 3 orders of magnitude. And so UF and FDOT are actually currently developing a new quick method for MWD for in situ soil and rock assessment using similar bit types. And I think a few of the other states around the country are also pursuing this as well. And so we feel this is going to be an ideal application for pre-bit borings. We also think it's going to be ideal to determine minimum tip elevations for driven piles with variable rock in driving conditions. So one of the biggest challenges that we're going to face, we're developing MWD in situ soil assessment. We'll be relating these drilling parameters to conventional soil engineering parameters like we've done for rock. However, we're already seeing agreement between MWD and conventional site investigation methods that are commonly used for soil characterization and design. This is very encouraging. So what we have here on the left-hand side is we have MWD in orange, and then in the blue and the gray or silver, this is CPT tip resistance. And so we can see that we have very good agreement between the profiles that we developed for MWD and CPT. And this was a very, very dense A3 soil. And we were pushing the limitations of our cone truck. Our actually first run with CPT, my field specialist said, I don't think we're actually going to be able to do this with the truck. We ended up blowing out our dilatometer when we tried to run it at this site in this depth zone right here. But MWD plowed through this no problem and gave us the same profile. And we could also see we ran SBT at this same site. We also have agreement here with MWD. However, SBT took a considerable amount of time to complete, and we're not getting the high resolution profile that we get with CPT and MWD. So now I want to switch over and talk about the board pile construction QA/QC side. This is what Dr. Dave Horhoda likes to call the low-hanging fruit of MWD. And it's because a lot of these drill rigs that we use to install drill shafts or cast piles, they already have all the sensors that we need to perform MWD already installed on there. So that's what I'm showing on the right-hand side here. I've just simply tapped into the electrical unit and I'm collecting the data that I need for MWD. And then directly behind this electrical unit, I've mounted my junction box for MWD. It's clean, it's a low footprint. It's not disturbing the construction process whatsoever. And then during the actual shaft construction, I can sit at a safe distance away and view the actual installation and monitor the progress of the drilling. So you can see I'm actually sitting behind the CEI team that's sitting over here out on the trestle. What I'm showing here now on the top right, these are profiles from a drilled shaft job that we did here in Florida. And so what we're showing here is the specific energy recorded in layers of rock. And the average distance between these shafts was about 700 yards. And so what we see here is a tremendous amount of variability, not only in the elevations where we encountered rock, but the strengths that we're encountering as well. So you can imagine if we were to run just one load test, maybe here at test shaft B, and we felt great that all we need to do is put these shafts down to minus 50 feet, we would have drastically overestimated the capacity at site A as well as site C. And this is actually the site that was the focus of that Graham et al. Paper, where they were telling us that, we have this very erratic bedrock, and it's very challenging to produce meaningful correlations with load tests. Well, if we look in these profiles up here, we see dashed lines. Well, these were actually mobilized sections that occurred during the load test. So during the load test, we mobilized these sections. So we were able to get a good measurement of the load tested mobilized side shear. And so what we do is we compare the average specific energy that was recorded in each one of these mobilized shaft segments, and we can directly relate the drilling parameters to engineering parameters that we would use to verify that this shaft is competent enough to support the loads that we think it is. So MWD is allowing us to produce a meaningful correlation with load test data that can actually be translated to our untested production shafts as long as we're using MWD for them. So let's say we're going to a production shaft at any one of these locations at this site. Well, now we have this amazing correlation that we developed from full-scale load testing and conducting MWD in the footprint. So let's say there's an area of concern, a 5-foot section or something like that, and the average specific energy was 6,000 PSI. We would go up, we'd hit the curve, and we're able to estimate that the average side shear for this section is 12 KSF, and that either satisfies our criteria or it doesn't. But we know this right away in real time. And so what we're doing is we're eliminating spatial uncertainty concerns that arise from Florida's high degree of subsurface variability. And MWD allows us to assess these conditions within the footprint of each of our production shafts at full scale. And this drastically increases the value of expensive load tests, as long as they're coupled with MWD, because we can take that very valuable information that we gain from one single location, and we can use it all throughout the site. So now I'm just going to quickly transition to MWD for auger cast piles and show you some variability over short distances. As they identified in that paper, we can have quite a bit of variability even within the same foundation element. So that's what we're showing you here. In this bottom left-hand picture, we can see a pile group of 16 piles, and the total footprint of this is 32.5 feet by 32.5 feet. And about 65 feet away from the center of this pile group is a test pile. And so what we have here in the middle is the specific energy profile that was recorded, where we're taking a measurement every 1 centimeter of penetration, plotted versus the elevation at which it was recorded at. So we can see from all the smaller lines that we actually have quite a bit of variability even within this pile group. And then the dark black line is the test pile. So we want to know how well did our test pile 65 feet away relate to all of our piles within this pile group. And so what we do see is some variability within the pile group compared to the test pile location. However, we're also noticing a correlated structure. So the test pile didn't always follow the mean or the median value from all the drilling that occurred within the pile group, but it generally fell within the max or the median. So that makes us feel good that this load test is probably going to be representative of this specific location.
Hey, Mike, we're going to have to wrap things up here.
Okay. Do I have a couple more minutes?
Yeah. Just take 2 more minutes to wrap up, and yeah, great.
Okay. All right. So what I'm showing you here is just a comparison of specific energy and then total energy at the top of from the test pile compared to the pile group here. So in orange, this is the average specific energy per 5-foot layer recorded in the test pile, and then in blue is recorded in the pile group. And we can see that at location B8 here, we have pretty good agreement. And then total energy is just basically a cumulative sum of the specific energy. And we can see that we have very similar values. So this builds confidence in our constructed pile that it's similar to the test pile. However, if we look at B1, we see that where at the test pile location, we had quite a bit of strength and rock, we actually don't have it at this location, and our total energy is actually reduced. And so this draws concern for the pile. But the great thing is, like we showed you, we can develop correlation between specific energy and rock strength, and we can actually measure or get a good estimation of the unit side shear for each one of these layers, as well as the pile capacity. So at B8, kind of speed through some of this, we had a capacity demand ratio of 1.58. So this satisfies the LRFD design and builds confidence that this pile can support what it was supposed to. At location B1, we had 12.8 feet less of a rock socket or competent rock socket compared to B8, and we had 554 kips less of capacity compared to B8. However, the C to D ratio is 1.07, and it still meets the demands of the engineering LRFD design, and it will pass our design requirement inspection. So one thing we've recently done for the FDOT is develop an ACIP pile QA/QC analysis tool where we can input custom drill rig specs, and automatically updates this analysis tool. We can assess specific energy, and we can assess unconfined compressive strength side shear when we have correlations developed, and we get an incredible amount of information that's immediately generated from this. And we also get a drilling profile that tells us where we were efficiently drilling, where we went wrong, where we can make improvements in the future. And our current initiative is to make this initiative or this information more readily available to stakeholders in satellite locations to speed up and improve decision-making when problematic site conditions are encountered. And I'm probably out of time at this point, so I'll just leave these conclusions up here.
Good deal. Thank you so much, Mike. Great presentation. This is just fantastic stuff on revolutionizing drilling, and what really is got my attention was the fact that the relationship between efficient drilling and quality sampling are connected completely, and so I think the transition is going to be a lot easier as we get into MWD. But great presentation, thank you very much. And we will get Rob Garfield lined up, and I'll introduce Rob. I also want to remind you that there is a poll currently open. If you haven't taken that poll, please do, and we'll be closing that in about 4 minutes. Rob is the owner and principal, one of the owners and principal geophysics physicist of Hager-Richter Geoscience, and has been working in the area for more than 19 years with in the geophysical profession. And Rob is a licensed professional geologist in the state of New York and Louisiana. He manages the Hager-Richter's New York, New Jersey office. Rob is involved in all aspects of Hager-Richter's work and specializes in high-resolution borehole geophysical logging services for geotechnical and environmental investigations. Rob, you have the floor, sir.
Great, thank you. So, yeah, what I'm hoping to do here and impress upon you is another option of all of these subsurface characterization techniques that are out there to better understand these geotechnical subsurface conditions before construction. And as others have mentioned, just like with the other methods, these are useful pre-planning, during design, during construction, and even during monitoring. So all different phases, but there's a heavy amount of information that you can get ahead of construction that will really reduce your unknown, reduce your risks, and reduce your costs. So my specialty is in borehole geophysics, and I'm going to breeze through that pretty quickly so you're not overwhelmed just with all the different methodology. But what I really want to focus on is integrating many of these methods. So whether it's surface geophysics, MWD, CPTs, borehole geophysics, or other traditional and new characterization techniques, where the real value comes is when you bring everything together and understand what's happening in the subsurface to paint that picture as true as possible of the in situ conditions. So what is borehole geophysics? Similar to what Phil discussed, where you can measure different properties from the surface using non or minimally invasive methods. With borehole geophysics, you do the same thing from boreholes that others have drilled, whether they are boreholes that have been drilled by using MWD methods or other traditional drilling methods, or if they're drilled shafts or foundation elements. Any boring in the ground, whether it's a water supply well or any of the other methods of drilling that we talked about, you can get characteristics of the soil, of the rock, and of the fluid. We're going to really focus in on the televiewer methods, which is an A-GaME method where you get images of the material. They are not inverted or modeled. They are true images, whether they're optical or acoustic images of the in situ material. You don't have the mechanical breaks and the washout that you get inside the core barrel or during drilling. This is the material that's left behind in the borehole wall that you can look at the conditions of. And that's both man-made, whether it's concrete, or if it's natural material like soils and rock. And then you can also measure the deviation of the borehole itself, because whether it's intentionally inclined or it was meant to be a vertical hole, you need to know where the borehole is, because the holes are rarely, there's no such thing as truly as a perfectly vertical hole. Why do we care about this? And many times you have an outcrop before you put a rock cut in, or you can see some of the rock. Well, if you want to characterize that material, where the actual cut was going to be, you want to actually look at that material. Let me see if I can get a pointer here. Let's say the cut is hundreds of feet or a mile back. You want to look at the material where your project is, and you want to get the best in situ understanding of that material. If you don't, as you start to do a cut, you might have these big rock falls, which can be dangerous to people on an excavator or on the roadway. And if you just core, you might have large areas where you have no recovery or it's completely chewed up and you don't know, is that the natural material or is that somewhat drilling induced? Also, geology changes drastically over short distances. You can see just over a matter of feet here, you have a fold in the rock. If you looked at a surface of the rock right here, but your rock cut was going to be back on this face, your orientations have completely changed. So when you're doing rock slope stability and different kinematic analysis, it's completely changed. So again, if you can put the boring in at the location of interest, you can get those true conditions right there. And this is kind of a nice flow, the way these presentations were given. You started with the surface geophysics, which can be done on a reconnaissance level as a very initial step to understand what's your depth of rock, what's your overall properties of the materials, the velocities, where do you have faulting and things of interest, so you can focus where to put those borings, where to do your MWD, where to do CPT. You can focus that. Now you put the borings in and you can start getting information from the borings. The equipment is extremely versatile and portable. We can work from a platform above a highway. We can work on an active construction site. We can work from the Arlington Memorial Bridge in Washington, D.C. This was the view from where the boring was put in. The work was done at night. This is the shot from logging in our van with the Washington Monument in the background. This is a shot from inside of that van, looking at the field tech on the outside of the van that put the tool in the hole. And then you get the data live. So as was discussed during the MWD presentation and the CPT, you see these images live. So you can see the bottom of the concrete abutment for the bridge. You can see this large open fracture zone where the concrete should have been in contact with the rock, as well as some natural fracturing. And this comes up live, and there's much more you could do back in the office with it, but you do get that initial understanding of the material right away. You can also do this from water. So this is off the southern tip, the financial district of Manhattan, working from a barge. If you can get the drill rig in there to do the drilling, the geophysical equipment is portable enough to get in. Again, now, instead of working from a bridge deck, we're working from an actual abutment under a highway bridge. There's also special case scenarios. This bottom left was for a project at West Point where they expected near vertical fracturing. So inclined boreholes were put in to better characterize those near vertical features. You can do this from above a tunnel to look at the material surrounding the tunnel and even into the concrete tunnel alignment along a highway in Connecticut here. And if you're looking for information and you can't access the borehole vertically, this was a case where you had a rock cut and they drilled in horizontally, and the borehole geophysics can also be done in these environments. I'm not going to spend too much time going real technical on the methodology just because there's not enough time for that. But this is a slide showing that when you look at televiewer images, what you have here is a cylindrical borehole in the ground. Any plane cutting through that borehole is then unwrapped into what we call the projection view. So a horizontal fracture would be a red horizontal line here. A vertical fracture would be a vertical line. But dipping features, when you unwrap that cylinder, create a sine wave. And we can take the measured diameter of the borehole over the amplitude of the sine wave to get the true angle of the fractures. And then the direction, because these images are oriented, of the bottom of the fracture gives us the dip azimuth, which is 90 degrees from strike of a fracture plane or a bedding plane or a foliation plane. The other thing that we're doing is we are measuring the angle and the direction of the borehole. So aside from being able to give you borehole deviation information and understanding where the borehole is located with depth, we also can correct these orientations to true orientations. So when you look at a rock core and you see what you think is a horizontal fracture, what that actually is a fracture perpendicular to the axis of the borehole. If the borehole is vertical, then it is horizontal. But again, if the borehole is off vertical, you don't know what the true orientation of that structure is. And with the televiewer data, the orientations that are plotted out to later do kinematic analysis or just better understand true recoveries and RQDs, the orientation side of that is corrected for any borehole verticality or deviation. Here's some real televiewer data. So you have optical televiewer on the left here, which is a true color image of the borehole unwrapped. These two images are both made from the acoustic televiewer. The first image is the amplitude of the acoustic televiewer, which will show differences in texture, roughness, density of the rock, while the second image, the black and white image, is travel time, and it will only show you an open feature where it literally took longer for the acoustic wave to go into that feature and come back out. You can also wrap this back up for 3D presentations to compare to the core, or to present to the public or non-technical clients that don't necessarily understand the unwrapped images, but still want to see the true televiewer data. Really quickly, just to show how high resolution these data sets have gotten, we're well over 150 to 200 feet deep in some of these images here in water. These were 6-inch open bedrock boreholes. And you can see when these were drilled, you would have lost all recovery in here, had no RQD, and would have no way to understand, is this a void? Is there rock there? What are the orientations of these structures? You can see the changes in lithology. In this case, they didn't even core, so the televiewer data was the sole way of representing what the material looked like. And then here's some optical data next to televiewer data. That previous slide was from some igneous rock, and this is in some sedimentary bedrock, again, showing you these open features, the orientations of those structures, and if you had any lithologic variation. Of course, there are limitations to the methods. You need a borehole to do it, but for the optical televiewer, it works in air or water within that borehole. But if there's water, the water has to be clear. For the ATV, it only works in water. So in this case, you had water just past 14 feet. So the ATV data doesn't start until 14 feet. The optical you have throughout because the water was clear. You could see some infilling on these fractures. And again, these colored lines are ways of representing the fracture orientations, which are later plotted in Excel so that you can pull these into different geotechnical analysis softwares. But again, by running both the optical and the acoustic, you have the kinematic analysis and fracture orientation information throughout the entire borehole. And in this case, it's the flip. You had water throughout the entire borehole, but where the water, so the water was 12 feet when we got there and you couldn't see through it. So in the air, we got great optical data. We then filled the borehole with water because it held water, and we got ATV data throughout. So again, by having both tools, we're able to characterize the entire borehole. So ultimately, you can do things like this: plot those fracture orientations, plot the bedding orientation or the foliation orientation, and understand, in this case, you have a primary fracture set that's parallel or subparallel to bedding, and a secondary fracture set that's steeply dipping and is roughly orthogonal to the bedding parallel fractures. So ultimately, this is one of the important pieces of information that you want so you can understand that rock slope stability and characterize what's happening in the subsurface, rather than going into construction without this information on something like a rock cut or an excavation and not knowing what the conditions are. And now you run into issues and you're trying to mitigate them in the field. You get this information in advance before construction, and you know the true conditions to reduce, again, risk, delays in schedule, and costs. And you can contour that data. Again, you've seen some of these pictures, getting this data from structures. So instead of just looking at the rock, now it's the exact same data we've been talking about with the optical and acoustic televiewer, but now we're looking at the in situ conditions of concrete. It doesn't matter whether that concrete is a few days old or 100 years old. If you want to know the true conditions, when you core concrete, it tends to break up and have more mechanical issues even than rock, unless you're in some really weathered material. So if you want to know if the concrete is truly in good shape, is it bonded to the rock? This allows you to get that in situ information. So you had some weathered concrete here at about 30 feet or 30 to 40 feet. And you had some pretty decent bonding between the concrete and the bedrock, although there was a little fracturing there. When they cored this concrete, it all came back broken up, and they were concerned about the condition of it. The televiewer logging was able to show them it's in pretty good shape. There's a few issues of concern, but overall it's good. And then the natural rock itself was actually highly fractured. It was a bigger concern than the concrete. Here's a quick example of a project we did for Ohio DOT, where they wanted to expand a rock cut along a highway. This is some of the conditions they ran into with some very fractured and weathered rock. When they cored, they lost, in some cases, entire runs of core where they had no recovery. They had very low RQD. They dropped the camera down and could see that there was some big fracturing, but the water was quite cloudy, and they didn't get any true orientations of the data from that. But we came in and did the televiewer logging. So this is the exact same borehole. You can see in this slide, we're 116.5 feet to 122.5 feet, which is this zone right here. And now you can see those fractures. You can see their apertures measured and get true orientation of those structures for the kinematic analysis. This is another example of a very steep fracture that they kept on seeing in the video, and they lost 50% or more of the recovery, never mind the RQD being next to zero in some of these cases. But we came in with the televiewer data. We could determine the actual orientation of that vertical feature as well as the cross-cutting fractures that were causing it to rubbleize. And then zoomed out a bit further, this is starting to put together some of the idea of integration. So now they have RQD and recovery from drilling as well as a description of the rock type. And we can plot that with the televiewer data and our orientation information. So you can see how low RQD and recovery drop down here, and it's right along that vertical fracture. And then it goes up a little bit where you only have this individual discrete fracture at approximately 86 feet. Then the rock type changed to a shale. And even though there weren't big open fractures, the rock itself was just much softer and broken up when they drilled. And again, they lost low RQD, although very good recovery. And we can characterize all of that with the in situ televiewer data. There are many other things that you can measure using borehole geophysics, as I mentioned earlier, whether it's electrical properties, seismic properties, properties of the fluid, of soil, of rock. There are methods that can see through casing, but we could also measure flow. So one of the things that's not always characterized before construction is you look at the soil, you look at the rock, but if you know water is flowing through these layers, that can cause additional weathering. It can cause issues with mitigation of water at your site. So these are important things to know. And the borehole geophysics can actually measure where there's flow going into and out of the material and at what rate. And one of the tools we use for that is something called the heat pulse flow meter, which is shown here, where there was no flow up in the casing. Flow came in through this fracture, connected to the soil, flows down the borehole at 0.5 gallon per minute, and then it flows out of the borehole. So again, at the bottom, we have zero flow. And that's sort of what you would put together for a heat pulse flow meter log. But what I really want to stress is the importance of that integration that I talked about briefly on Ohio DOT. So whether we're integrating borehole geophysics with MWD, with CPTs, with surface methods, with other traditional testing and lab testing, you typically have all of this data in different presentations, in PDFs, in Excel, in different web portals, in GIS and in CAD. The more you can integrate this information, the more you're going to be able to get out of it. So real quickly here, I just want to show you what we put together as what we call an integrated borehole log. Don't feel the need to try to read all of this. I'm going to do some zoom ins back in PowerPoint briefly, but I just wanted to show you what a full deliverable would look like. So this was done from a dam and roadway. It was an inclined borehole that we show here with the stick up and the angle of the hole at 29 degrees. We show a site plan right in the header, and then we show all this rich data content. So this borehole was drilled with MWD. So we have the core locations, we have recovery and RQD, the coring rate, a bedrock description, drill mechanics, including rotational speed and pull down pressure. We have fluid observations, including pressure, volume loss, fluid color, relative turbidity. We have many borehole geophysical methods, including the optical and the acoustic televiewer, the fracture orientations. We have natural gamma ray and some electrical methods that tell us about changes in lithology. And then we have the temperature and conductivity of the borehole fluid. We have transmissivity measurements taken by either Packer testing or other continuous measurements. And then we have the flow meter logging with the heat pulse flow meter. Finally, we have Packer test results and a final well construction. So you can see here, they wanted to put in a piezometer. So we show the construction, the grout, the sand pack, the piezometer placement, and all of this rich data content side by side. So now going back into the PowerPoint, this is the MWD and drilling component. And you can see there's some rich, great data content as was provided in the previous slides. And we're in open bedrock, but how do we put all of this together? So what you can see here is there's a coring rate increase. So you assume maybe you have some fracturing. You see the RQD decreases. There's some description of the rock here. And you can see there's this very large change in pressure and a decrease in the volume loss. So what's going on here? This is over such a short interval. Is this real? Was this just due to a mechanical issue during drilling? But look what happens when you bring in and integrate the borehole geophysics with the MWD. Now you can see right where you had this pressure change. There is a near horizontal fracture that we had already identified from the borehole geophysics as a water-bearing fracture. There's an estimated transmissivity from some of the hydrogeologic testing, and we had flow into I'm sorry, out of the borehole under ambient conditions. And when we pumped, flow came into and up the borehole. So again, now we have a really rich data set just by integrating it. Instead of just having the mechanical measurements, we can now put that all together and understand the orientation of that fracture. Here's another zone. You can see the coring rate significantly increases as you enter this zone, and then there's a very discrete change at 154 feet. I really commend the guys that did the MWD on this. They also took great field notes. They mentioned, hey, we had some frozen lines here, so ignore this data set. We changed the drill bit at 155 feet. So this increase in coring rate wasn't just geologically controlled, it was a fresh drill bit. So you have to understand all these things rather than just looking at the measurements. And then again, you put it together with the borehole geophysics and you see you're in some weathered fracturing where the coring rate increased, it's sped up. You can see you have some changes in the RQD and recovery and some of these fluid property changes at these fractures that were hydraulically active based on the borehole geophysics. And again, just one more zone showing the same thing, increase in coring rate, decrease in RQD, changes in fluid properties, and again, a shallowly dipping fracture identified in the borehole geophysics. We know the orientation of it. We know the transmissivity of that feature, and we're just really starting to put things together. And finally, again, a major decrease in recovery in RQD, large weathered fracture zone, and we have all the orientation of these features and an identified flow zone based on the borehole geophysics. Bringing it all full circle, we come back and look at some surface geophysics. You're monitoring soil properties, rock properties, top of rock. You bring in information from drilling. You do things in an iterative approach where the surface geophysics on a reconnaissance level shows you where to take CPTs, where to do drilling in MWD. You focus that further with additional surface geophysics and maybe borehole geophysics, and you start to pull that whole picture together. You can create contours of the rock surface, the water table surface, boulder zones, weathered zones, and you can start bringing this together in 3D on 3D plots that are brought into GIS or CAD or other 3D representation. You can also integrate from land to marine. So here's a case for a future bridge where top of hill was monitored during some marine geophysics, and then top of rock was displayed in both marine geophysics and surface geophysics. So here's a case where we have surface geophysics along the landmass, and then the marine geophysics in the water. Again, you're integrating that. You can look at features between boreholes. So now we're looking at cross-hole seismic tomography, where we're looking at the velocity of the material, whether that's rock or soil, in between two boreholes. You can find voids, you can find man-made tunnels, you can find karstic limestone, top of rock. Again, all this information, because you're looking at high resolution data, but you're integrating between boreholes now and introducing the information from conventional methods. Again, you could introduce ground truth from CPTs or MWD, and then you can also finally bring together things like borehole geophysics as well as surface methods, where this is an electrical resistivity plot shown behind acoustic televiewer data, and you can see where you have this large change in the electrical properties of the water and a fault where water is flowing, and you can see each spot where that intersects the borehole, there's a large fracture of interest. And it just brings it all together so that ultimately you're providing this information to the client, to the owner, to the DOT, so that decisions can be made for design, for construction, and then you can continue that process during construction and look at things temporally to see how things change when construction starts and to monitor construction. So again, if I've impressed anything upon you, all of these methods have their advantages, they have their limitations. You have to use it as a toolbox approach to get the most comprehensive in situ characterization of the subsurface, so that later you can apply them to projects like you're going to see in the case studies and presentations this afternoon.
Fantastic. Great presentation, and looking forward to talking more about how these techniques, really can help us improve our characterization in routine characterization for construction decisions and constructability. Thank you very much, Rob. I'm just wanting to first I want to thank all of our presenters for a tremendous job on providing an overview on these techniques that give us, sort of the springboard into the problems that we're going to be talking about during the afternoon. So first up, we're going to have Jim Cuthbertson talking, and then I'll be talking just to show what WashDOT does, and also where the problems. I'll be focusing on problems that we typically see in site characterization on construction, and then we'll go into discussion at that point. So we did a poll. I will show those results when we return after lunch. It is straight up 1 o'clock. I thank you so much for being here for this session, and want to see you back at 2 o'clock. So thank you very much. Welcome back, everybody, or if you're just joining us, welcome. And we are in our second part of our second session, super summer session. And before we took our break earlier this morning, we were discussing the types of methods that we have available to help us better characterize conditions. And we're going to talk now about what WashDOT, their experiences are with construction and characterization of those types of problems that do come up. And I am also going to be talking after our WashDOT presenters. And so I just want to let me get down to here. Yeah, so just a reminder here that we are recording all of these sessions, and that we will be our presenters and our panelists during discussion and during presentations obviously have views, and those are reflective of their own views, and any discussions that we have are exactly that. So just those views are not necessarily those of FHWA or its contractors. So keep that in mind. And so earlier this morning, as I mentioned, we talked about the methods, and now we're getting into the case history type discussion here. And our first presenter, and I'm going to minimize my screen and allow Jim to jump in here, but I'm going to go ahead and introduce Jim, and we'll get things rolling. Jim is with the Washington State Department of Transportation, and he started his career in 1991 in the geotechnical office as the state foundation's engineer, and was in that position from 1998 to 2019, so over 21 years, and he then changed his role into the state construction office, where he's the assistant state construction engineer that for the office that supports the Northwest region of the state. He's involved in construction, contract development, administration, and dispute resolutions. And we also have, I'm not sure if Andy or Andrew is going to join us or not.
He was supposed to join us, but I don't see him on the meeting.
Okay.
I'm here. Can you hear me? But I'm
okay.
listed as Jim Cuthbertson because we shared invites. So
Gotcha. No, well, I will go ahead and introduce you. And Andrew Fisk is the state geotechnical engineer for Washington State Department of Transportation, and he's worked with the department geotechnical office, managing projects from concept to construction for the past 18 years. Andrew has also worked in the private community, consulting community, and he has also worked as a civil engineer in design and construction for the Illinois Department of Transportation. So Jim and Andrew, you have the floor.
Well, greetings, everybody. I am Jim Cuthbertson. I am the real Jim Cuthbertson. And so I was going to lead a lot of this talk, and Andrew's going to participate as well. Before I talk about some of the A-GaME stuff, I did want to give a little background on how Washington develops its construction contracts. So we are divided up into 6 different regions in our state. I happen to support the Northwest region, which is the corner down there shown on the image. But we also have mega programs, and what those are large corridors that have got hundreds of millions of dollars of funding and multiple projects slated for them. They are our 405 program, our 520 program, the Alaska Way Viaduct, which was where we did the big tunnel bore. We also have another mega program called Gateway, and we're looking at adding another one that deals with the Columbia River crossing. So we have these sub programs. So regardless, what I'm trying to say is there's a lot of different silos of excellence in our agency that are producing contract plans, and they kind of do it autonomously. And what they do is they will then tap our centralized specialty groups in our state. Geotech is one of them. So we have a headquarters centralized geotech. We have headquarters centralized bridge office, hydraulics, environmental, right-of-way utilities. So all these people in these regions will tap these specialty people to help them assist with designs and putting together contracts and things like that. And then, like most state DOTs, for our actual contracting, we do 2 main types: design bid build, which is our bread and butter. You know, that's where we put together the plans and specs and we put it out for a competitive bid. And we also do design build. We've been doing design build. I think the first one we did was actually 2000 was the year that we did that. But it's been part of our program pretty hot and heavy since about 2010. We've done only one progressive design build project, and only one GCCM, but you know, we are looking to expand our use of both of those methods. And then, of course, we also do emergency design or emergency projects, flooding, landslides, things like that. So in our contracts, we have a bunch of geotechnical information, and this morning's talk was about the geotechnical information that we collect. And in our state, what we do is we have contractual geotechnical information and we have reference. So I'll let Andrew explain a little bit about the differences between those two.
Sure. Thanks, Jim. So it's a lot of times it's about interpretation and also the quality of data. So we have a collection, as most states do, of some great historical information from construction along our roadways, whether they're boring logs from the 50s, 60s, field records from the 20s. We've got a lot of great data. However, things may have changed since that data was collected. You know, the highway was built, or other developments may have occurred. So that's data that is useful for design, but it's not contractual level data. You know, we collect data for upcoming projects, that data that is current, that has accurate X, Y, Z that we can, you know, place in space, and groundwater information from, you know, recent years. All of that information makes for great contractual data, stuff that we as the DOT will stand behind. As for reference information, those boring logs that we have a pretty good idea of where they are in space, the XYZ, but maybe not super confident on that. Or, you know, possibly they're now underneath 20 feet of roadway embankment. So things may have changed a little bit through settlement, consolidation, things like that, that are useful for a designer, but not something that we're going to stand behind. We'll include as reference for our design community, whether it's a contractor and a design bid build, or our design build team and the designer, and you know, those types of information we provide, but as reference. There are certain other types of projects, for example, fish passages. We are currently working through billions of dollars of fish passages, opening up culverts to allow for salmon runs to be restored. And in those situations, we do allow contractor design of buried structures, so really big culverts, and the adjacent wind walls. And so when we're doing that, in order to expedite the project, we will do the geotechnical work in-house, provide a report, and that becomes contractual for the contractor to give to a designer to design those buried structures and wind walls. So that's the only time that a geotechnical report is a contractual document, the only types of contracts. Otherwise, all of our geotechnical reports stay as reference material because they have interpretation. Jim, I don't know if you want me to continue on with talking about this or whether you would prefer to talk on the contractual side of things.
No, I think you covered the contractual pretty well. The one thing that we did not touch upon was the GBR and the GDR. So with design build jobs, we are producing a geotechnical baseline report, which is not a geotechnical report. It's a whole different critter. And basically what we are trying to do when we set our baselines for our design build jobs is have a very definitive baseline. It'll be something like in the shaft excavations, you will encounter 5 boulders greater than 6 feet in diameter. We try to put specifics to it. And so if they hit 2 boulders, 3 boulders, we've told them you're going to hit 5. When they get to number 6, then that could be eligible for a differing site condition claim. And so we try to set baselines that are definitive, that they are, there's no ambiguity in them, so to speak. Because anything in our design build contracts, you can get change of conditions compensation, however you want to look at it or call that, if something is different than how we portrayed it in our baseline report, or something is different than what's in our data reports.
And in the data report is just data that is high quality that we feel comfortable to stand behind. Otherwise, it goes into a reference. Anything that requires a lot of interpretation, such as geophysical reports, pit tests, things like that, will all go under reference.
Yep. So let's talk a little about the A-GaME technologies. Our state does do cone penetration testing. And I have to admit, it probably is one of our underutilized exploration methods. We have a lot of gravelly soils, a lot of tills, things like that, and a lot of urban areas where, it's difficult to get access and it's difficult to push. All of the stuff that you heard this morning from Gerald, anyways, we do use it. We just don't use it enough. We do seismic and electrical geophysics. We have the ability in-house to do seismic refraction and surface wave stuff. We do not do electrical, though. We do not have the equipment to do electrical resistivity stuff. So that is something that we often contract out. We do have our own drill crews. We run our own drill rigs. We are just in the process of swapping out one of our older rigs and getting a new one. And while we were at it, we decided to add on the measurement while drilling technology. So we've got that coming. And we've been using optical and acoustical televiewers for many, 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 many years. So I do want to talk about real quick about a fish passage project as an example to kind of talk about our approach to A-GaME and our approach to contracting. So we have this I-5 Secret Creek fish passage job. It's going to be about a $35 to $40 million project. We're going to be building probably 3 bridges. Right now we've got tiny little culverts that cross underneath the highway. They're barriers to fish. And so we're going to open those up, build bridges, and open the channel up and reconstruct a whole bunch of stream that we buried under I-5 embankment. Right now, this project, what originally started out to be a design bid build project, but just recently in March, as a result of a value engineering study, we decided that probably design build is the better approach. So we've changed our course of delivery on this project midstream, and we're going to talk a little bit about that. Just so you know where it is, up in the northeast corner of our state. This is a simple little graphic showing you the existing stream comes underneath northbound I-5 over here, comes through an existing little culvert, flows through our median, and then exits out the other side. We're going to build some bridges and open this all up. So what do we have for geotechnical information? So we went into our files and pulled open the drawers and went, geez, we don't have much here. We don't have anything here, actually. So when they built these culverts, they probably just threw them in the bottom of the gully and threw 20 feet of dirt over the top of them. No geotechnical design whatsoever in the 50s or 60s whenever these were built. So what we decided to do is phase geotechnical approach. We had no information, so we decided we needed to get some. So we went out and did a couple of geotechnical borings. Of course, the geotechnical borings that we did were just standard, so there was no measure while drilling on this. And of course, in the geotechnical world, things are different, right? So we have variable depth for our refusal materials where our glacial tills are. We have, you can see there's two different elevations for where the water tables are. You can tell by the different elevations at the top of the borings that there is some grade separation between those lanes. But all in all, we've got some variable site conditions. So, all right, what are we going to do? So geotech pulls open the geology files, and we look through our Department of Natural Resources, who has a library of geology maps, and decide, well, we need to get some more information, so drill more. So this is what we elected to do. We ended up putting out 12 additional borings out here at this site, and at the same time we wanted to instigate a geophysical program. So we were originally planning to do the geophysics and the additional borings kind of at the same time, with the idea that as the geophysics data came in, if we needed to shift borings to go hit something that was a little suspect, we could do that. We could add borings, delete borings. We're going to kind of do it as a in hand together kind of a thing, but as luck would turn out, yeah, we couldn't do that. We had issues with getting our geophysical contract on board, and we ended up doing all the borings in September, and we weren't able to get our geophysics on board until January. So we're a little out of sequence A-GaME wise. We're still kind of A-GaME in that we have geophysics and we have boreholes. You'll notice we didn't do any CPTs. We probably could have at this site, but so what did the geophysics find for us? Actually had some good data. If you look at the data, there's some culverts. There was actually a tributary culvert that didn't. I didn't have a blue line on my little figure, but anyways, so this was looking through the northbound resistivity and the shear wave. Again, this is the southbound lanes. So how did this progress as far as A-GaME? February, we were doing preliminary drilling. September, we did a second round. In January, we did the geophys. If we could have done it more A-GaME, if we could do this as a do-over, we probably would have done it with the geophys probably first and then planned the drilling. But that's the way that happened. So what do we have for geotechnical information? So I mentioned we have all those borings. Now this is what I wanted to talk about. Now we switched our method. So we're going to be producing a baseline report, and we're going to be producing a data report. We've got enough information that we feel we are confident in being able to identify zones of soil that will be prone to caving. We are confident we know where the difficult pile driving is going to be because we know where the till is now. So we can develop some pretty good baselines for the design builder to use in the development of the project and in their bidding. What are we going to include in the data report? And I did see in the chat that somebody was asking, or one of the questions, what about geophysical reports? Those tend to have a lot of interpretation to them. And you have to recognize that even our geotechnical borings have got interpretation to them as well. And so Andrew and I are still going to probably have a little discussion about how confident are we in the geophysical data. Is it something that we want to include in the data report as data? So it would then be subject to change of conditions claims or differing site conditions claims. Or do we want to relegate the geophysical to reference? Some of that depends on how variable the site conditions are, what we think the risks will be if we do it one way versus the other. And so we're going to have some discussions and figure out where we're going to stuff that thing, whether it's going to be a part of the data report or is it going to be provided as reference. You want to add anything to that, Andrew?
No. So to give people a little bit of a perspective, so we did the second round of field exploration, both the drilling and the geophysics, in order to prepare for value engineering on this project. So we had a multi-day high-level review of where we were going to take this project for, whether we're larger bridges, buried structures, and that's when the decision was made. So we used this information to inform that decision to change project delivery types. So this was really valuable in order to inform that discussion. So that's really what I was going to add, Jim.
All right.
That's some background.
Ben did want me to talk about some cases where we had a less than desirable outcome. So I scoured through all of our change orders for the last 5 years and found this example. So you'll see that this is a pretty current contract, and in fact this contract isn't closed yet, but this issue is resolved. So in August, we issued a change order on this particular project that added 9 days and $277,000 into the contract to deal with unsuitable subgrade material that was discovered underneath the existing lanes and shoulder areas on this project. And one of the things that reasons why we elected to authorize this change order was we kind of had a contract error in that we didn't include quantities for removing this unsuitable. So we identified this material, but we didn't include quantities for it. So let me talk about that. So I mentioned that we have reference and contract information. In our contract, this is the section where it talks about the reference information. So we told this contractor that we do have a geotechnical report, we have some piezometer data, and we have a stormwater general permit, and those are all referenced. So those are made available for their use, and any interpretation or use thereof is their responsibility. We did have borings that were in the contract. So this is a excerpt that I grabbed out of the geotechnical report, which was reference, okay? And the only reason why I grabbed this reference figure was because it showed where we actually had borings and where the work was occurring. So some of these areas where we were having soft subsurface conditions, okay? So actually the borings that are in here are included in our contract as contract documents. But this exhibit, this aerial figure, is out of the geotechnical report, which is reference. We also, in our state, produce this thing that is called a summary of geotechnical conditions, where we try and take the geotechnical information, boil it down into something that a contractor could understand, and provide that to them so that they are at least made aware of certain conditions. And one of the ones that we have, so this is what one of those documents looks like. I highlighted this
for design, bid, build projects.
This is for a design, bid, build project. So what we did say is throughout the project, there's near surface soils that have enough fines to become soft and unsuitable when wet. And so, Mr. Contractor, you better plan on encountering this material. So in terms of our contract, we've disclosed these conditions to our contractor in the contract documents. We have geotechnical borings in the contract that show silty sand, 3 blow count, near surface, got a high water table. It's only, 4 feet below the ground surface. So as far as we were concerned, the unsuitable materials that they were encountering are not a differing site condition on this contract. But like I pointed out, we sort of failed to include the quantities for removal of that material, disposal of that material, importing the new. And so we, being good partners, said, yeah, Mr. Contractor, that's a little bit too much work for us to assume that you've distributed across related bid items. Yeah, you're probably due some additional compensation. So we wrote the change order. So is this a A-GaME failure? Yeah, not necessarily. Could we have improved our geotechnical information on this contract? Yes, we probably could have. Hindsight's 2020. A little bit different phased approach would have probably let us target some of these areas with problem soils. We probably could have utilized CPT compenetrometer or some resistivity to better identify them. Shear wave velocity could have helped us on this. So there's things that we could have done to improve this. Here's another one. This is just a simple, quick little one. This was on a little $1.1 million contract. We issued a change order for $7,000. This happens to be a fish passage project as well, but there was a farmer that had buried an irrigation line we knew nothing about, and the contractor encountered it on construction, and we ended up doing some GPR to locate it. So this is just what happens to be in the contract. We had 2 borings. We were doing this basically culvert replacement job, this little $1 million job, and we hit this utility or irrigation line that we didn't know anything about. So that was really all that I really had to present. So I am open. Andrew and I are open for questions, or Ben, you can just take it over.
There is one in the chat. What are the advantages to the department of including the geophysics report to the GDR? Is the question. And so an advantage of, if we included the geophysics report, we would be providing some contractual information that would better define the subsurface conditions for the project. We are opening ourselves to, in my opinion, or we could be opening ourselves to a bit of change of conditions claims if they were able to link the geophysics report and the conditions reported therein to something different that they found when they go out and drill or open it up.
Yep. So on that point, and I think you're bringing up some fantastic, great presentation, by the way. fantastic and great lead into the discussion coming up here. You talked about GBRs, and it sounds like you're using GBRs exclusively for design build projects at this point. And there's
we do have that thing called a summary of geotechnical conditions, and it's akin to a GBR. It's not as definitive. It's the usual how to put this tactfully. Us geotechs like to cover your butt statements sometimes. The contractor should expect to encounter soft, silty soils, or caving is expected in this unit. Put those things in geotech reports. But our geotech reports, the contractors weren't always getting that information, so they go out to drill a shaft or whatever,
right? And
they'd hit this caving soil, and they'd be like, "Soil's caving. It's a DSC," right. And we're like, "No, we knew it was going to cave. We got borings. It's 4 below count sand. Of course, you need slurry or casing or something, Yeah. And so we decided we were going to create this thing called a summary of geotechnical conditions. So it's not contractual in that it directs the work of the contractor. So if we wanted casing, if we were going to require temporary casing, we're going to have a contract requirement that requires temporary casing from a certain elevation.
Okay.
But if we're open to, casing could be used, slurry could be used, we're going to leave it up to the means and methods of the contractor.
Right.
We do want to alert them to those risks that, hey, this zone has the potential to not stand open. Casing may be required or slurry may be required. And we want to tell them that. So we created this document to do that. So it's kind of baseline, but not really.
The other thing that we do is we define engineering stratigraphic units. So those soil units with similar properties that are out at the site. We define those in the summary of geotechnical conditions, and then per boring, we provide a top and bottom elevation.
Okay.
And so if the contractor is then out there and they find material that's substantially different than what we've defined in that summary of geotechnical conditions, then we're open to we're willing to negotiate different site conditions.
That's interesting. That's very interesting.
But we also use it to protect ourselves too, right? So we've defined those conditions, and as long as those conditions are what the contractor's encountering, that also affords us some level of protection too, right?
Gotcha. Yeah. Yeah. So, the interpretation nature of geophysics, and it is largely, there's a lot of interpretation, based on, because there's not a unique solution to geophysical results. So there is interpretation required. And, one mechanism that, we've started talking about is that we could actually do that interpretation and come up with a baseline report. And it sounds like we can use that also to inform us on what did you call this other mechanism?
We just call it a summary of geotechnical conditions. We take the geotechnical report, boil it down to a 1-pager is what we're trying to do. Gotcha.
And it is a contract document.
It is a contract document.
Yeah. So, it sounds like that's the first time I've heard something other than a geotechnical baseline report being used as a contract document like that. But,
it's kind of got that flavor, but it's not as definitive.
Yeah.
It's not going to say, Mr. Contractor, you're going to hit 5 boulders in this shaft, or soils between this elevation and this elevation are liquefiable. We're putting those kinds of things in a design build baseline report so that there is no argument about do they need to do ground improvement or liquefaction mitigation for bridge foundations or embankments, things like that.
I see. Well, that is a great mechanism to know about. And on the design or the geotechnical baseline report, we are going to be, for the people out there in the audience, we will be talking about that in session 3, going into a little bit more detail than how that could work. And maybe, we could, re-up this discussion with a summary. But
Well, maybe you had to get somebody else's opinion. You know. It's not. We aren't the only game in town. I mean, there are 50 states.
but we
no, we'd be
certainly
happy
appreciate hearing your opinions and your experiences and how just it's very helpful for many agencies to see how other operations take place. And then when we get into session 4, when we're talking about how do we make this happen, what are the mechanisms like you're talking about here that we can actually use, that's on the table to proceduralize in our day-to-day type, bread and butter type work.
Sure.
So great. Thank you very much. And I've got some other questions lined up for you, coming after.
We'll hang around.
Hang around.
Good deal. So I am going to queue up. Are you seeing you're seeing the wrong presentation. Are you seeing a presentation, anybody?
Not yet,
just your
Ben.
video.
Not
See
yet?
you.
Okay. I think I have 2 presentations up, so it's
Yeah, right now it's just your video camera, not the screen share.
okay. Thank you very much. Let's try this one more time. Let's try this again. Well,
What's happening when you try to share, Ben?
Pardon?
What's happening when you try to share?
It
Oh, there you go.
Are
All
you
good.
seeing screen 1?
You
No.
see black now.
Yep.
Try again.
It changed my screen. Let me maybe look sideways here, but you're seeing it now, I think. Right?
That's the one.
Okay. So yeah, it just switched screens on me. Yeah. So what I just sort of leading into our discussion and following on what Jim and Andrew have shared here, I wanted to make sure that we were understanding the geotechnical uncertainties that we have and that occur in construction. And it coming from me, it's a little easier for me to talk about cases that I've seen, and I'm not going to, in the most part, I'm not going to be talking about where those projects are. There are a couple of cases that's easy to talk about, but anyway, I want to talk about the geotechnical uncertainties that impact construction and constructability. I want to first just point out that the presentation that I'm giving here has no effect or force of law, and it's not meant to bind anybody in public in any way. The presentation is intended for information and leading into this discussion. And the other part here, and I think I did a good job with the zoning out things, but FHWA, the U.S. government, does not endorse products or manufacturers, and so any trademarks or names that appear in this presentation, you can consider that being part of for essential part, or it's not meant to endorse anybody, and so they're included for informational purposes and don't reflect any preference or approval or endorsement from of any one entity or product from the U.S. government. So what I want to cover here are those geotechnical uncertainties and the sources of issues that we have during construction, examples of those problematic conditions that we have in construction, and then how we can improve. And we've seen some of those methods. So, just a lead in and a teaser to that discussion part. So, I think I mentioned the very first part of the session this morning, most of the time when we do site characterization, we are often focused on, what we need at the moment. And it comes in phases, right? There's sometimes at the very beginning of a project, we don't have a lot of information about the project requirements or the performance that we need, for those structures. So we learn more as we go along, and doing one phase is certainly limited, and it limits us to be able to do what we need to do as we understand better the site characterization, especially as we're talking here in construction. So the fact that sometimes you can hear people say, well, we've got the information that we need here. We'll, as far as constructability, we'll deal with that in construction. Or you might hear somebody say, we'll just design conservatively. And those have obvious impacts, right? The fact that if we're dealing with it in construction, we still have those uncertainties. And if we're designing conservatively, something that we don't always consider is the fact that we're over designing. So they're going to be bigger foundations or bigger, more than we need. It's more complex, and it's a more complex design, and that means more risk when it comes to actually implementing the construction of those elements. Very commonly, not always, but you can understand this if you look at drilled shafts and the fact that a 4-foot diameter drilled shaft is a lot easier to construct than an 8-foot diameter drilled shaft, and it's a lot easier to construct than a 12-foot drilled shaft. The complexities are exponential, and so if we go with the mindset that we're not going to characterize for constructability and design conservatively, we're adding additional risks on top of those uncertainties that we're talking about today. So just keep that in mind. So, nearly 50% of the project problems that we have on our transportation sites are either directly or indirectly related to how well we characterize geotechnical conditions for design and construction. Of course, we're talking about construction here, and where we often fall short is on providing contractors with enough information to bid on, where we actually get competitive bids that aren't all over the place, and also allow those contractors to effectively carry out the construction that they've been asked to do. This information comes from the NCHRP Synthesis 484, and there's probably not a lot of mystery here that we do have problems, and these are very common problems of material quantity busts and groundwater, which is mischaracterized or it's just not characterized in cases. And that's one huge area where we certainly can do better, and it is a source of a lot of our problems. Misclassifying or mischaracterizing materials, and this goes into variability of materials and those uncertainties that we could introduce if we don't characterize those as well as we need to. And then rock, we have problems with rock because rock, we have different opinions and ideas of where rock is, and the material properties vary so greatly. And we'll talk a little bit more about that here in a bit. So when we're talking about foundation challenges, you're seeing a couple of pictures here. one of artesian conditions where we have the set, the casing set high to maintain a head and make sure that our hull is maintained. And you're seeing variability of ground conditions here where piles are sticking up. So this is after driving. So obviously there was a lot of variability here and a lot of stick up that suggests that maybe this wasn't the type of pile or the foundation type that probably was, would have been better suited, at this site. But every ground condition is going to have its challenges, from running sands and silts to, the compressibility and the time rates of settlement and setup and poor pressure distribution or poor pressure dissipation. All of those are elements that contractors, would be very helpful for us to understand those impacts before we get to bidding. And what you're seeing here is an example from Derek in his past career here from Minnesota, where they had a soldier pile wall, or they called it a king pile wall. But going into construction, before they got to construction and final design, they recognized the fact that they had variable conditions out here and that their plans of having embedment, pile embedment links in certain areas wasn't going to work. So just having that uncertainty removed and having the understanding that going in here, we're going to have to do something different in this area, saves a lot of headache. So groundwater, as I talked about, this is one area where traditionally we have not done a great job with. And there's reasons why. Part of it is kind of laziness and the fact that part of it's schedule, and they're real problems. But the fact is this is very important information, and we're seeing that by the frequencies of problems that we have with groundwater. And pretty much every geotechnical issue that you have is going to have that interaction with groundwater. So understanding those conditions are incredibly important. What you're seeing here is a case example of a highway. It was a new section, and you can see the old section to the bottom of this picture, and the new section is the part that has filled. So this was under construction. It was already paved, and they were working on another section. And when this filled, and what did they know? What did they not know during this project? There was very little information in this section about the conditions, let alone the groundwater conditions. And there were some looking back at what they did have, there were some telltale signs that there was water involved here. And if you looked at the topography information, you wouldn't necessarily know that we're going to have groundwaters. But when you start digging in the reconnaissance type information and the desk review and start looking at Google Earth, for instance, and you're seeing this highly vegetated area around here, this wishbone type growth of trees, there's quite a bit of water, and that's has been there for a while. And then you start seeing areas digging a little bit more, springs. And then if you go into the hydrogeologic data, which is actually in this case was very easy to find, you recognize quickly that this was an aquifer system or around an aquifer system that was daylighting in this area, and other telltale signs of ponds and whatnot that would give you the heads up of that we probably need to be looking at groundwater conditions here. And you're seeing groundwater in this picture, if you can see my cursor. This is after failure, And this isn't, this is standing water from groundwater flow. But this wasn't the case in construction. During construction, talking to the construction engineers, they said they did not see signs that would think there was a problem with groundwater where they needed to put under drains, into the system. And so, that's the importance of actually doing the desk study and finding out the information with piezometers and other things over time, because it's pretty obvious that this was water driven, and that, you're seeing water. This is just right down from the scarp where water's coming right out of the scarp. So we could have problems with weak foundation soils. They don't have to be thick layers. It could be just a thin lens of material, and as the diagram or the cartoon alludes to, it's not a very big layer for this transitional type failures to mobilize. And the picture that you're seeing here was on the surface of probably a harder clay layer, but it was probably weakened by some water as well, and there was probably some other influences with the water pressures as well. This happened from the time the tension cracks showed up to the time there was a headscarp of 6 feet, was weeks from occurring. So weak incompressible materials, so not just weak, but we can have those bigger layers of soft materials that can cause us problems with differential settlements, on the performance side. But our contractors need to know this type of information for staging of our embankment construction, if that's part of their means and methods of constructing the embankment. As the far right picture you're seeing, you wouldn't know that was related to compressibility, but it was. This is a side hill fill where the materials below the foundation materials were in fact compressible, and you're seeing tremendous amount of mobilization at the top and shearing occurring in the fill because of that. So again, these don't have to be big, and this is incredibly hard to find, this type of material. The last example I showed you, CPT information, could really help with this. In this case, having televiewers and having MWD, the ability to get quality samples where we're not washing out materials within joints, can help us tremendously, because you can imagine with a double tube core barrel in an environment like this where we had a failure with an MSE wall that was translating on a very thin layer of a clay within sandstone, and that could be easily missed with a double tube core barrel washout from the quality. And with MWD and what Mike was talking about, the quality of samples that we can get now, understanding the fact that there's this relational of quality to efficient drilling, really is, I think, going to be a game changer. And not only that, we have other methods to sample in materials like that. But easy to miss, but we have the technologies to help us with that. In this case history, this is actually in Vicksburg, Mississippi, across the Mississippi. So adjoining Louisiana and Mississippi. And this project was built, I'm thinking back in the 80s, maybe originally, but in early 2000 is when the structural engineers said, we've been seeing movements for a long time on this bridge, and over time, the collective movements, were numbers of feet. But at each movement, the increments, so it was slowly creeping, would be an inch or two at a time. But when they got to this point in the early 2000s of, feet of displacement, and they knew this was a geotechnical issue, and they had been dealing with this problem structurally by, doing retrofits on the bridge and opening up finger joints and whatnot. But they called in the geotechs in the early 2000s on this project. And you can see sort of the directions of movement. This is a very complex geology, and we have this interaction with the Mississippi River and the Vicksburg Bluffs, and the big Vicksburg Formation and the Los Bluffs above that. But this is geology almost in motion compared to many other geologic features and episodes that we see. It's not thousands or tens of thousands of years where this is happening. This is happening in a lifetime. In fact, the Centennial Cutoff that happened before the Civil War, the Mississippi River went right through Vicksburg. That got cut off in the early 1900s. So this movement of the river with the bluffs and the angle of attack on this bluff, over time, you can imagine that this bluff has seen a lot of interaction with the river, and that's exactly the case. And what you're seeing here is a generalized interpreted profile of what was going on here. You're seeing the Los Bluffs, and then below that, the Glendon Formation, and then this Mint Spring Marl, which if I remember correctly, we've got some water. There's some tard and aquifer action going somewhere in here. But then we get into this Forest Hill materials, and you get into some clays and sands interbedded. And what during the initial investigation, they were doing standard penetration tests, and in some areas they were getting 50 below materials within this Forest Hill clay. And so in the materials, the bad actor here was this material that when you start shearing it in its residual state, it gets down to friction angles of 6 degrees, 6 and 10 degrees, which just truly bad actors here. And other areas that are mobilizing that have these same shear planes within them. So it gets pretty complex as far as what's going on, but I have to give credit to all people who have done work on this project for characterizing it and understanding the conditions systematically over time, what was going on here. So in this case, what was going on was these very weak lenses and the interaction of the level of river. So when movements were occurring, it's when at a low river stage, or essentially a rapid drawdown condition, but it's not really rapid. But they know very well, we know very well when those movements are occurring. So right now, it's been monitored, and they have protocols in place, for safety. If movements are more than expected, then they will shut down the road. But they are in the process of actually doing some rehabilitation and remediation for this project. And so, not an A-GaME technology net per se, but we always want to use the tools that we need to determine, what's going on here. And in this case, we've got some really very hard, very stiff to hard materials, and we have this weak shear plane that's going on within them. And if we're trying to push a UD tube in it, it's not going to work. But we can't push a cone, and we can easily miss this with just about any other tool. But we need to sample this material, and a Denison sampler is the type of tool that we can use, or a pitcher sampler, where we have a triple tube type core barrel that that's offset where the cutting teeth are a little bit higher than the undisturbed tube to get these types of samples that we can take into the lab. So don't forget the more fundamental methods that we have at our resources to solve our problems. Rock, as I mentioned, is a big problem. And, you know, part of that is if I ask a geologist or I ask a geotechnical engineer or a structural engineer or a contractor what rock is, obviously I would get different answers. And that's because it's not a very easy thing. You know, it's method or application kind of controlled in many cases. And, you know, in fact, it brings up the question, do we, using one term called rock for a material that varies from, you know, 1,000 PSI to 60, 80,000 PSI, hugely different materials. Is it appropriate just to use a term like RQD for fractures and maybe unconfined compressive strength? Good index test, but we have much better methods of characterizing conditions. And this brings up sort of the question of how we use pay items and terms like rock or competent rock. Very frequently I get that question, you know, what is competent rock when it comes to a foundation, and, you know, where, you know, we place the tip of that foundation. And it's specific to geology and the areas that we're in, and we could have very different materials in a site or across a site, even in many cases. So one lesson learned that I had personally, this comes back in the 2010 era, 2008, the ARA projects, if you remember, were Recovery Act type projects, what they called shovel ready projects. So they were, you know, on the shelf or shovel ready, you know, ready for construction. They just typically are less risk in their nature as well. And this was a widening project. And I think it's reasonable to think that in most widening projects, we're not doing a lot of construction here. We're widening things out. And in this case, we had a cut, and the you know, contractor was out here doing work, and at some point he started cutting the slopes back more than what was on the plans. And that's when I got the call on, you know, where, you know, is this justified? The contractor obviously thought it was unsafe or unstable. And so went out there and we looked at what the report said and what information was available. And the report said, I think reasonably, you know, for this type of project where we had cut slopes already there, we knew what the performance was of what we saw on the faces. The call was made that they were going to cut those back to what was actually done originally. And that's by itself a good place to start. But the question that I had, or, you know, while I was asked, was, is this reasonable? So my next question was, well, where's the other data? And there was very, very little. In fact, you know, in this area, I don't recall, there probably was some information from the original, you know, construction of it. But the problem here now is you have a contractor who's under contract and he's excavating materials and he's getting paid by the yard. And so widening or, you know, sloping this back isn't a bad thing for him. And so, you know, is this justified? Well, I could not answer. You can't answer that if you don't have the information and the analysis behind that. So what I suggested naively was, well, we don't want to make this mistake on the west side, which they hadn't started working on, and it was slightly, different materials at this point, where you see, limestone and sandstone interbedded, daylighting out of the slope toward the slope, and you're seeing just the opposite on the other side, where you're actually getting into shale, and that was, I think, part of the question, the original question. But you're seeing the performance here of a ditch, and you're seeing rock that's being caught in the area. But it's all in all, there were a couple of places that, I thought maybe would be a problem, once they actually start cutting this back. But really, what are the conditions? And so they did an investigation here. That was what we didn't want to make the same mistake. And the problem, the naive problem here, is the contractor is in the driver's seat at this point. This is not the time to be doing an investigation, because there's delays. There's what are the cost differences of doing a redesign for this, that at this point probably could have been more efficient. But where the contractor was, getting paid by the yard isn't a bad thing, and sloping it back is going to perform well, and that's ultimately what happened here. I think in some parts of the slope, it probably could have stayed where it was, and they were planning on plenty of catchment area there for this slope. But it's the lesson learned here is, once you're in construction, and in this case the contractor was in the driver's seat, we're just sort of spinning our wheels here on what types of decisions are going to be reasonable. So karst features and variable conditions, source of a lot of our issues: void, sinkholes, cutter and pinnacle. If you're familiar with karst features, and there are, I think, just looking at the survey results earlier, it looks like 25% or somewhere thereabouts do have karst issues, and that jives with what I would think, based on how much we see karst within the United States being problematic, and but it's not just karst. You're seeing a sinkhole, or not a sinkhole, but a void, actually, within this, right below where our foundation is placed on the right picture. And then you're seeing cutter and pinnacle type geology in Alabama here, which just incredible variability across. And I can't remember exactly what was going on this specific project, but I do remember this being, one of the issues is that there was a lot of variation. They had to figure out what was going on during construction. It caused some issues, but variability can come from just going across landforms that are different, or residual geologies that have weathered rock to fluffy silts to hard ringing rock in very short spaces, mountainous terrains, and other complex geology, which is sort of a catch-all for that variability. All of those can be sources of these types of issues. And when we have these types of issues, we need to be thinking about just how will we characterize that variability across the site. And you're seeing a great picture here of cutter and pinnacle in eastern Tennessee, just feet away from one another. But you can imagine the challenge of somebody who thinks they're going to be driving piles in this kind of environment. This is pretty incredible. And so this was close to the surface, but this could be further down in the profile. So there's a number of methods that we saw earlier this morning, and we have the opportunity to improve the way we characterize conditions. And I've listed a number of areas where we can do it, from the rock and the bad actors. And I'm going to sort of walk through a few of these as we sort of wrap this up. So, on the excavation, the rock characterization side, as I mentioned before, we have materials that vary from soft muck to hard ringing rock. And, what we call rock might have unconfined compressive strengths of a few thousand PSI to 80,000 PSI. And, that's just one index that doesn't tell you anything about fracture frequency or faults or structure that are going to play a huge part in keeping a hole open, during construction. And so that brings back up the question, is RQD alone going to tell you everything you need to know? And obviously we have descriptors typically in logs that do have specific meaning. But what you're seeing here are methods that we have now with MWD, downhole logging, including televiewers and suspension logging, borehole radar, not to mention surface geophysics. But measurement while drilling, of course, is new to us, but it's not new to many other areas. And in fact, in the mining industry, they've been using MWD to inform them on drill and blast operations, on the spacing and the charges and the orientations that they need to drill. And so I think there's a lot of crossover that we can learn from them. And there's no doubt that the concepts that you saw Mike talking about, and now that we know how to control, that drilling efficiency has such a huge part, not just in the quality of samples that we get, but in the quality of measures that we get as we're doing those measures, so that we can get those interoperable, variations that we're seeing. So all of these are in our toolbox. When we come to groundwater, the fact that we have this CPT and dynamic pore water pressure measurement that can inform us on those things like, setup or spacing and sequencing of pile driving, and are we going to have problems with sequencing of material driving through some clays that are not very conductive hydraulically. We have methods that are not just geotechnical, or not just A-GaME, sorry, bread and butter piezometers. And again, we don't characterize groundwater good enough. And I think we really need to ask ourselves when we're on our projects, how important is understanding the groundwater conditions for this project, and do I need to include piezometers, on this project for the purposes of both design and construction. Testing, borehole testing that we don't do frequently, from pump testing and constant head, all the way to the stuff that you saw Rob present on logging, on transmissivity. We have the abilities to get this information, and what Rob was showing you was pretty fantastic. The fact that we have the ability, you're seeing a version of that on the side there, side by side, we have all of this information from the fractures and the formations, the information to the geophysics information and to the physical testing that might be done with Packer testing and transmissivity. And of course, surface methods can help us characterize groundwater flow direction and show us changes within, a profile where water might be. Bad actors, variability, ground improvement, all of the technologies you see here are A-GaME related, and the ones that provide physical measure of CPT, MWD, televiewers, those are all continuous, and that's incredibly powerful when you look at if variability and bad actors, if we're looking at that thin layer, we can use these types of technologies and to better understand before we get to construction. And then those surface geophysical methods, seeing variation across a site, and where we might want to do more exploration to understand those conditions better. So ground improvement is also, thrown in there as part of what, when we're getting into construction, what are the conditions and what are the performance requirements, and how do we measure the difference there? When do we know that we've achieved what we need to achieve? And this is just one example of how CPT can be used to provide pre and post improvement operations for a project. Again, MWD, when Mike sort of touched on these elements, not anchored systems, but the drill shafts and the auger cast in place piles, really coming along. You see Rodgers' work, Mike's work here on, again, this drilling efficiency. If you're looking at this high flow rate, which happens to be in this case, the more efficient situation here, you're seeing very, very good correlation for this relationship between specific energy and unconfined compressive strength. So taking that from what we can characterize during geotechnical investigations before we get to construction and applying to that during construction. In fact, a contractor can use that to inform them for those anchored systems on incline drilling, the same technologies. I haven't seen cases for it, but I'm sure that there is application there. I've heard of incline drilling operations using MWD. Yeah, so we're back to just sort of wrapping up things here. We can improve our investigations for these types of areas, characterizing rock, groundwater, variable conditions, and informing us for requirements during drill shaft construction to inform us what kind of materials that we're getting in, which is an advancement to we have methods. We have a way of counting blows when we're driving piles and getting an index of what kind of resistance measurement while drilling is going to help us with that. I'm not going to talk about visualization or bidding. We're going to get into that in session 3, but just wanted to sort of finally push this one slide and to get you thinking right now about our discussion that we're going to start right now, on the types of problems. And you can do a screenshot on that. I'm going to have the ability to pull this up later if we have, if we want to look at the types of challenges when we're discussing. But there's a number of those, and in all of those cases, we have the tools to help us before we get to construction to remove a lot of those uncertainties that cause these types of problems. So with that, I am going to sort of switch gears. I'm going to ask if we could all our panelists to turn on their screen so that we can have a good discussion. And I'm going to pull up the intro slides here just to get us started.
And while you're doing that, Ben, I want to mention to everybody, since you had commented on that last slide, I am happy to send people copies of the slides. You need to just email agame@geiconsultants.com and request them. I'm not going to send them to everybody, but I'm happy to share them with people who request them. So if you want to review things or just remember, just let me know.
Excellent. Thank you very much. So, one thing that we haven't done yet, and we had a poll, we asked 5 questions early on that I think probably are a good place to start. Thank you, Mary, for putting those up. And the first 2 questions really had to do with phased investigations. And so this is somewhat of a practical matter. 100% people agree that is good, that, when the need is there on complexity or risk or need, they see value there. The second question sort of leads into that, and I think you're going to have to scroll to see all of the options there. But looking at the what is the most significant obstacle performing multiple investigation phases for a project, and based on the choices that people were offered, schedule shows up there high, and this is pretty much the way I wrote that question. And actually, I guess those answers follow in sequence. Yeah, from what I've heard, many people say it's really the construction schedule. Budget there 25% suggests that is an issue. Convincing people that they need more investigation, about the same amount, and those certainly are the common talking points that I get asked, or that come up from that. But just to start out this discussion, on phased investigations, how do we solve this problem?
And maybe the whole issue of cost and budget issues and convincing management. You're aware, we at DFI, we have the Increased Testing Saves Money webinar series. And there's overwhelming evidence that if you do more soil investigations, in the end, you are going to save money. And what I always ask clients is, when they say, well, there's no money for that, there's always money to pay the claims. There's always money to cover the cost overruns. But there's never way less money available up front to do some additional site investigations. And if you need some examples, we're more than happy to share that from the Increased Testing Saves Money webinars. If you have examples there. But I think what we need to do is really showcase and then highlight those specific examples to clients, so that people are aware that doing more investigations, knowing more upfront, will save you a heck of a lot more down the road.
And obviously, you're preaching to the choir here.
Absolutely.
But so who do we need to do this? You have examples that show savings.
What we have done within DFI on purpose, and normally these webinars are free for our members only, but we have said that all the owners and all the DOT management can come free of charge to see these examples. Because I think it needs to be to a higher level. It's not the audience per se that you have here. I've heard project managers and construction managers, but I think we need to go a level higher and really start saying, hey guys, this makes perfect sense. And it's not like outside consultants. And one of the things that, and Mary can talk more about it, she and Georgette have looked at data within the Corps of Engineers. And there were overwhelming evidence that if you do more investigations up front, it saves money. Outside groups, there's a study that is often quoted from the UK that shows the same thing. But I think we need to go to a higher level, really the top of the DOTs, where we really need to convey that, hey, this just simply makes sense.
Good point. Any other thoughts? What we're doing here, obviously, is I think a big audience that needs to be aware that scheduling and budget are an issue, and that we can save money up front. Certainly is that upper management, but it's also the project level folk who are not geotechnical engineers, who they do this day in and day out. To see something different
one other thing that you could add, and I alluded to it in my presentation. And when I was the VP of engineering, I always looked at a construction schedule, a schedule for a project, that there was sufficient time between freezing the site plan and figuring out when your detailed design had to start. So that once you knew where you really needed your loads, because quite often we do a site investigation kind of in the area, and with a bridge, it's a little bit better, generally speaking, but you know where your piers are going to be. But quite often we do a site investigation and we kind of try to figure out what is the bearing capacity or the soil conditions in the area. But once you know where you need your highest, where you have your highest loads, where you really can save money on optimizing your foundation. And you showed a picture in your presentation about some piles that were sticking out pretty far. Well, I'll dare to say that probably the nearest site investigation was probably a couple of
Yeah, it wasn't there.
feet. It wasn't there. And even though they knew that is where you need to design your foundation. And if they had done an extra sounding there at the location of those piles, it would have cost more, but it would have saved much more by getting now the piles to the correct length.
Yep, definitely.
Yeah, I think that obviously it's case by case exactly how having the better information is going to save you money and how you're going to use it. But I think that what everyone, I would hope, can agree upon, whether it's those of us that use these techniques regularly or those of us that are out contractors in the field doing the work, whether you're using it or not, you see that when the conditions that you come across are what you expected, the schedule stays on schedule, the budget stays on budget. When there aren't unknowns and unnecessary risks taken on, everything benefits with time. Time equals money, but then there are also true fixed costs, in that these are all methods that can guide you to get that truer picture of the in situ conditions so that you know what to expect. It's not about, sometimes it's about getting data that's more applicable, whether it's the MWD, and you optimize the drilling so that you get the true conditions because they're better than you think they are, or it's a condition where there's a bad condition, even though you don't want to know about it, you're better off knowing about it early so that you can maybe change the project alignment, or if the project alignment can't be changed, you do some sort of ground improvement or mitigation. So there's so many different levels at which having all the multitude of subsurface characterization information benefits the project, and all of that in the end saves time and money and risk.
I agree with you, Rob. What we're finding a lot of benefit of, and we've finally convinced the powers that be, is that early on in a project to get the SMEs, to get the geotechs involved. And whether, if we don't have any historic information going out, and we might not know exactly where our structures are going to be, but getting some subsurface information in order for them to right size the project, it saves us and it saves them, and it creates a much better constructed product when we're not under the gun with a fixed add date for a project that we're finding all kinds of geotechnical surprises as we start to better define the geology out there. So
I think it's a really good point. You talk about bringing the geotechs in, and one of the things that I've been working on, and many of us on this call have been working on, is changing the culture of including that geotech team, including geophysicists, because one of the things is you could have geotechs that have really good experience with geophysics, or DOTs that have some of the capabilities in-house. But if you can get a geophysicist in the room early so they can say, hey, you guys might not be aware of this, but this method could actually tell you this about groundwater. We do this in the environmental industry all the time for contaminant transport, but it's applicable to highway geology and geotechnics, or maybe we do this in the tunneling industry, but you guys could be using this for your foundations. There's a lot of information that, rather than writing a scope that says this is the geophysics that should be done, I know that for me anyway, with the clients and the states that I work with, I don't charge anything to be in that room to give advice. And then you have that information, whether I do the work or not, at least you know what's out there. But also it allows me to better understand as a geophysicist what you're actually trying to get out of it, rather than a scope saying I need top of rock. When what you really need is top of rock and ripability and shear, compressional wave velocities, groundwater. There are other methods we may have thrown at it if we didn't just read a spec and write up our costs and our proposal to what was in a spec, when that wasn't the full picture of what was needed out of it. And then also there's that approach, like you just said, when you have so little information, that iterative approach that seems on the front end to be slow, I find to always be the fastest, because now you do reconnaissance level investigations to maybe guide where your project ends up going and to give you an idea of what the means and methods and design might be right off the bat, because you have some rough ideas of depth of rock and strength of the soil and rock. And then you focus the more invasive traditional methods and then some of the more A-game methods. And again, it's just an iterative process all the way through the monitoring phase once something is installed.
Jim, you have your hand up.
Oh yeah, I just wanted to comment on, a lot of this information is a lot more sophisticated than what we've provided in the past.
Yeah.
And so, there is going to be a learning curve for some contractor to take this information, digest it, and use it effectively. But that shouldn't deter us from providing it, right?
Right.
So, I mean, we do want to give our contractors the best available information, because
That's a great
we
point.
as owners, we don't want to be the ones that are dictating means and methods.
Right.
It's always to the agency's benefit to work in the realm of performance-based specifications and delivery of projects. And you have to give the contractor enough information so that they can choose the right equipment, the right means, the right methods to rip that rock. I mean, or excavate, or drill that shaft, or put in the auger cast piles, or whatever it is, right? Anything that's going in the ground, it's just hard to do. And the more information you can give contractors, the better off you're going to be.
Yep. Very good.
And one of the tricks is communicating that, right? I mean, I know that that's a future session, but it's so important, because I know we've all talked a lot about what's interpreted and what's hard data.
Right.
Well, many geophysical methods are interpreted, but many of them, a televiewer image is a direct image.
Right.
Versus doing something like ERI, where you have inverted data, or cross-hole seismic tomography, where you're taking data, you're inverting it, there's non-unique solutions. So it's about communicating between the geophysicists, the geotechs, the owners, the regulatory agencies, so that there's open communication, so people know what is interpreted, what isn't, at a level where it makes it most useful, and no one's taking on risk that they're not realizing.
Yeah.
Or underutilizing something on the flip side.
And just to add to that, I think also that communication needs to happen throughout the project, not just in the beginning, when we come in and characterize the site and then we hand over the data, but through the process of interpreting that data, as you just said, Rob, and then as they're actually doing the investigation, doing the construction, what are we actually seeing? How does that maybe change our interpretation in other portions of the area or the site? So it's important to be that whoever's involved in the team be involved throughout the process. I think that's something that's key to stress as well.
That's a great point. And it goes back to communication, which is pretty much the root of pretty much all our problems.
Always.
Well, it's not only communication, though. There's another aspect, and I know it's not maybe the topic of this session, but education is there as well. I think one of the things that we need to do, and it goes beyond educating the people that are working in the industry right now, it also goes to the educating the students at the colleges and universities. When you look at the textbooks that they're using for geotechnical engineering, are they really up to date? Well, I don't think so. There are a lot of them describe methods that were state of the art many, many years ago. But I think we can all do our part in really making sure that those universities deliver students that are aware of these new methods and see the value of this whole thing, because then when they enter the workplace, they will automatically start saying, hey, why don't we do this? Because I've seen the examples where it pays off.
Right. So, if we make this the normal, where this is being communicated, because when I was in school, there was not a lot of discussion on site investigation. It was a lot of theory, on soil mechanics. And when I got into the graduate level, you did have that, but now not only are we talking about the the methods themselves and what they can do for us, but the fact that we have these methods that can do more than just design, but provide information for construction, and removing those uncertainties at that level where the construction guys in school may not be paying any attention to to that type of stuff.
I think it's really funny or interesting when you talk about the educational side, especially within the geotech community. What I found when I go to universities to lecture or do a webinar because a professor brings me in is they're either super current cutting edge where it's not ready for consulting, it's not ready to be applied on these types of projects, or it's really antiquated. Right. It's the stuff that we're actually using right now that there's a gap on, and that's a shame because it's great for the graduate students to be doing research on what that next equipment is going to be 10 years from now that changes the world in the way that we characterize the subsurface, but they're not always getting what the true approaches are that are actually being used in the industry.
Yeah, that's a great point. And to Gerald's point earlier, talking about the U-GaME versus the A-GaME, underutilized tools, there's nothing new about CPT. There's no doubt about that. But when you're looking at measurement while drilling, in other industries, the technology, the concepts have been there. We haven't used that for site characterization. And when it early 2000s, looking back after about 2014 is when it caught my attention. And I started looking back, and there was literature there. And it kind of surprised me that, this incredible, why are we not measuring as we're drilling? It's kind of a no-brainer to me, but what does that information mean? And that's sort of the point, and to what Mike is working on right now, and how far we've come to understand that relational information is still work to be done there, but we're making a lot of progress in the A-GaME came at the right time for MWD to jump on, where geophysics had been mature for many years, CPT. So yeah, I think we're in an exciting time, and I think bringing this up, I agree with everything I'm hearing here, on the educational side and the awareness side that we need to do.
Yeah, Ben, the MWD comment that you made, it kind of brings back with the example I used. That was an inclined borehole, almost 30 degrees from vertical to a couple hundred feet, and it was a geotech project, and it was still to this day the most sophisticated MWD setup. With those are just some of the parameters I showed on that log. We have other versions that have more. That was done in 2012.
Is that right?
And it's still to this day the most sophisticated MWD. We did ODOT where there was some MWD information brought in from that example I showed, but I've still yet have one where there was as comprehensive of a data set as what we had in 2012. And I'm so glad to see these presentations and what Mike's doing. And I hope to see it more, because it was so valuable in that project to guide drilling, but also to integrate with the borehole geophysics and all the hydrogeologic tests that were done for the piezometer design and so on and so forth on that project. It was highly successful, and then we just haven't seen a lot of it again. We've started to see it more on drilled shaft projects where, again, as it was in the earlier presentation, shown that equipment's already on there. We're actually starting to see some clients provide that to us on jobs where we're both working on.
Oh, that's awesome.
But I'd love to see it more and more. It's a really valuable and, again, underutilized method.
Very good.
So I got something else to add. I'd like to talk just for a second about, with the advent, or with the start of using load and resistance factor design methodologies and the resistance factors for geotechnical, there is the ability within the current AASHTO code to make adjustments to resistance factors if you can account for site variability. And a lot of the A-GaME methods, that is what they are geared towards doing, is helping you quantify or get your mind wrapped around the variability of a site And so there are direct benefits of using the A-GaME methods, better characterizing the site, and potentially using a little bit better resistance factors over just base code. So you can have some direct cost implications on your designs by shortening up piles or shafts or whatever.
But I understand that AASHTO is still looking at that. And when you say the ISO code in Europe already has it implemented, if you do one CPT or you do 5 CPTs, you can take credit for that. So it would be nice if that whole process within AASHTO can be accelerated because the knowledge is there, the awareness is there, the theory behind it is there. It just needs to be written in the AASHTO code.
Yeah, and that's in the works. That is in the works. So, and you know, what Mike has been doing with MWD and recognizing coefficient of variation and, you know, bringing that into the measurements, you know, that's truly in sync with, you know, what we're talking about on the design side. And, you know, you certainly could see that on the verification side and construction as well. So I think this is pretty exciting. So I want to get to the other poll questions, but I think we got plenty of time. And there was one question that was asked earlier in the question and answer that I thought was great, and I certainly want to get to that. But I do want to remind other people out there in the audience, if you do have questions, please put those in the question and answer, or if you have comments, feel free to put those and share your views in the chat. So in question 3, we're asking, you know, which of the following issues have you experienced on at least one of your projects? And, you know, what we're seeing, if you're looking at those results, are I would call them all significant. You know, you have everything from, I guess the highest rated was groundwater challenges. And I think that is, wasn't originally what I, you know, thought before the synthesis 484, that really pointed that fact out, that people were having some groundwater issues. And so, yeah, that being at the top doesn't surprise me, and variations with pile tips. I think just with the sheer number of, you know, that being part of our bread and butter, certainly sounds drill shafts about the same, soft or material, softer or harder materials than expected, and site variation pretty much about the same, which you'd expect. You know, challenges with unidentified planes of weakness and whatnot, not as big of a thing. Difficulty in excavation, which I'm glad to see there, but still significant, 33% or 34%. So, you know, all of them certainly significant. Is there any, you know, takeaways that you guys see from those results, and, you know, how A-GaME should, you know, where we can, you know, make changes easily in what we do for those? And I'm thinking back to Rob's, you know, one of his important messages coming out of that is collectively in our investigation, when we're doing multiple, you know, investigation methods, and we're piecing together, characterizing that site, that brings into view, you know, the interactions between groundwater and, you know, these other things that you know, it paints the entire picture. And, you know, I just want to bring that point back up.
The only thing there, Ben, what would have been interesting, because you asked here what kind of issues have occurred on one of their projects. It would be nice to get a second data point there to show on how many of your projects did it occur. Was it 10% of your projects or 15% of your projects? Because then you come back to what Rob was saying earlier, or somebody else, that once we know that what the problems are going to be, we can do something about it. And if we start seeing that on a large percent of projects, there is going to be some problem, then in and of itself, that's already sufficient reason to do a more advanced or more elaborate site investigation, because then you can address those things up front.
Yep. And just a confession here that we were thinking actually of that question here, but to do a poll on that with the other format, it was not going to work. But I totally agree with that. That was I think that would be very important information, or better, more precise information than that. The question 4, if we're going to that, how much impact do geotechnical uncertainties have on project budget? And we're looking at almost perfect bell curves, it looks like here, right? And that's true for the schedule. You're seeing, pretty much the same on both there. So, and pretty much what I kind of expected, that we're about there, and 50% of our problems we know where they're at. And so bringing that down and actually is probably a perfect segue into the other question that was asked earlier today in the question and answer pod. Someone was asking, is there a quantitative way of measuring and presenting risk because of these uncertainties and the cost of extra exploration and data collection? So can we actually see the risks of these uncertainties and the cost of doing exploration to mitigate those uncertainties? What are your thoughts on this? And I have one broader solution here, but I want to hear what you guys have to say.
Yeah, I had mentioned in response to that it's very case by case, obviously, but I could just give a couple examples. In every type of geophysics has a different cost. It depends on where it's being done and if someone's mobilizing for it, or if you have the equipment in-house. But just to put things in number perspectives for those that aren't familiar with some of the costs can be, if you're doing a project where you expect bedrock to be pretty level, depth to bedrock, or even the velocities of the material, and you're basing your design or your conditions that you expect on that, so you put a series of boreholes in. If you have hundreds of feet or even tens of feet in between those boreholes, you can do 500 to 1,000 plus feet of something like seismic refraction in one day. So you could do thousands of feet of seismic refraction for under $10,000 to $15,000, just to put a very rough number on it. So you guys could actually answer that question for yourselves. If you ended up having 2 borings, and one boring said rock was 20 feet, and then the next boring rock was 40 or 50 feet, and you assume that you just connected the dots, and then you go to put piles in, and now they're not where the rock is not being encountered where you expected. Seismic refraction could answer that question for a pretty insignificant cost, versus what happens out in the field when you have to then stop. Do you have to get more materials out there? Do you have to get designers back in? What are those costs and schedule delays, just by not spending an insignificant amount of money up front to know what's happening in between the borings? Or if you did the geophysics even before you did any borings on a reconnaissance level, and now you know where to focus those borings so that you get the most appropriate data that you need, instead of just saying, I'm going to scatter 10 borings along my site, see what I get. Maybe you only need 5 because the geophysics says it's actually very homogeneous. You can use less borings, but here's the important places to put them. So it doesn't answer the question directly, but I think it gives some of those that don't use these characterization techniques as often the information that they would need to understand how it could save time and budget.
I think Phil showed an example in one of his slides where we've an approach we've used to classify risk. We use it on several different applications and projects, and this was a resistivity data set, I think, for karst. And we divided it up into basically three categories: no risk, moderate risk, and potential for severe risk. So
yeah,
that's typically what we're able to do with the geophysics.
Yeah, my agency commonly uses CRAs, cost risk assessments, I believe is the acronym that we call them. Anyways, but yeah, it's kind of a, I don't want to say difficult thing to do, but they always come to the geotechs and say, well, you know, what's the risk that what's the likelihood or the risk that you're going to hit boulders in the shafts? And then geotech has to go, no, 10%. And then they say, well, what's the potential delays? And then it's like, well, it could be 2 days, could be a week. And then they say, well, what's the potential cost? You know, and so there's a lot of subjectivity that goes into those. But it is a tool and it is a way to help people quantify the risk. And I do know that FHWA, and I think if you go to Google and you search for CRA type stuff, you'll find lots of resources. But I know my state does. We do use them. There's a number of consultants in the area that that's one of their bread and butter things is they like hosting those. They facilitate those types of meetings. They got some fancy software they dump all the data into and then push a button and boom, it's like geophysics. They get a fancy plot of risks that come out at the other end.
Well, it's funny you mentioned that. Let me ask you this as a question to what you were just saying. I would, as someone that doesn't run those, I would assume that those CRAs are a lot more accurate when you have some reconnaissance information about.
Oh yeah. The most definitely, yeah. You need something to base those types of decisions upon. So
yeah, so I mean,
don't get me wrong.
Yeah, there's a point where the reconnaissance geophysics or any subsurface characterization at a reconnaissance level can be used literally to decide how much more you need, and it benefits itself on so many different compounding ways.
Another piece that we do, so, you know, characterizing your site is very important. The best characterization you can do is great. And then you have to link it to properties, right? Parameters for those soil parameters. So you can't separate out a well thought out lab testing program as part of this, right? So we're talking a lot about how do you characterize the site with all these different tools, but don't forget, there's a lab component that will really, you know, correlate or get those soil parameters for that unit that you just found. And so, you know, that there's cost there, but it's, you know, we try to communicate the benefit of having really good specialized testing to collaborate this information that we're gaining.
And that's where the data integration is so important too, right? If you take a soil boring and send something to a lab, that doesn't mean anything if you don't have a site plan that shows where that soil boring is. Well, why not take it to the next level and show other testing that's been done in that same location or nearby that you can start bringing the full picture together?
Totally agree.
Yep. Yeah, so I think things are headed that, you know, one thing that we're kind of missing is the fact that we don't have those measures, right? We don't have those quantified numbers that say, you know, this level of investigation, you know, provides, you know, this type of value, you know, on average. But there are, I think, some surrogates there that we have, and I think the risk register that was, you know, using those types of tools where we can you know, come up with a more qualitative, but there's a basis for those. But then the more qualitative, and this is, we're kind of wrapping this up. I'm going to share my screen because you all in the audience, if you were watching let me just make sure this thing is presenting. wrong screen. Let me, I am not sharing, right?
Not yet.
Not yet. Okay. Let me try this one more time. Share. There we go.
There we
So
go.
you all saw this in the slideshow. This graphic and what the Army. Oh, I didn't mean that to cycle through there. What the Army Corps has done is actually start plotting their projects on this chart to start, how much, if we're putting this much into our investigation, what's the reduction in project cost? And this is, I think, a first step and it certainly, I think, is, if you show this to, people who are making decisions, who are visual, this certainly grabs me, that there is, we're not talking that this upper bound has any really significance. We just put that upper bound there to say that might be there, right, with the question mark. But, from the data that we have there and from the data that actually the Army Corps has started populating, the data is in there. We're typically, 1 to 3% of the project cost, and, a couple of more, percent in that upfront investigation certainly could save us a lot more. But how much is sort of the question, right? And that's sort of the question that was being proposed. If we do a little bit more investigation, can we see that? And at least this is suggestive of that we can, with a few more percent, really reduce the risks that are related to a lot of those, uncertainties there. And with that, with 4 minutes to go, I want to thank all our panelists for terrific presentations, terrific discussion. I think this was absolutely great. Great thoughts here. Our next event here is going to be on August 17th. We're going to be bridging the gap, and we're going to be talking about the communication side of this issue, where we, have geotechnical reports, and that information resides somewhere and not necessarily contractually. And we saw a new tool here today with Jim that, brings in, there's probably worth looking into other mechanisms as well here. But yeah, we're going to be talking about the communication and how our geotechnical data is communicated to those contractors for bidding purposes and for their use in making informed decisions. And the fact that we have technologies today, we're in the digital age, we're going to, talk about some of those things as you're seeing. The visual model that you're seeing here is a lot more easily done these days because we have data and we can throw data into, this, into a model that shows CPT in this case, and standard penetration test, and you see electrical resistivity in the background there, and we're seeing that all together. So I hope you can join us for session 3, where we'll be talking about geotechnical baseline reports and other methods of communicating, not forgetting the fact that we do have to deal with this factual interpreted issue as well. So please join us on August 17th. Shortly after that, for our owners, we're going to be having that get together discussion a week later to talk about how we get this done, making it happen, for collectively, talking to one another and learning from one another, as I did here with Jim, on methods here and bringing that to the table. So I think that's going to be great. if you have any questions, please feel free to contact me or Derek or Silas from the FHWA side. Be glad to hear from you. And, we just can't say enough how much I appreciate the involvement of our speakers today. And, all industries help, from Gerald's work with CPT and the users group and Phil's work with the users group on the geophysics side. I think we've done a really good job communicating and really now, getting to our project managers and construction managers and getting that communication, bringing them to the table, and hopefully have those people there during that final session to inform our decisions on what actions we need to do to make this happen. So thank you very much, and look forward to seeing you on August 17th. Thanks, and take care.
Thanks, man.
Thanks, everyone.
Thank you.